Right now, somewhere above your head, the light from a star left its source 4 years, 2 months, and roughly 17 days ago. It has been traveling ever since, crossing 25 trillion miles of absolute nothing, passing through a darkness so complete that the nearest atom of hydrogen drifts alone in a volume of space the size of a small room. That light is arriving at your eyes tonight. And the star it came from is the closest one to our sun, the closest one. That word closest is doing tremendous violence to the truth, because when astronomers say Proxima Centauri is the nearest star, they are making a statement about ranking, not about distance. They are telling you it is first on a list. They are not telling you what first means. They are not telling you that first in this context still places the destination so far beyond human reach that every spacecraft ever built, every engine ever ignited, every speed ever achieved by any machine carrying human ambition across the solar system falls short of bridging the gap by margins so enormous they resist honest comprehension. 4.24 light-years. Say it the way a science documentary says it, with quiet authority, a slight pause after the number as though the figure speaks for itself. 4.24 light-years. It sounds manageable. It sounds like something. It sounds in the way that all precise decimal numbers sound like a problem that has already been half solved simply by being measured. It has not been half solved. It has not been 1% solved. What it has been is named. And in the human habit of naming things, we have made the mistake we always make with vast distances and deep time. We have confused the act of measurement with the act of mastery. We know how far Proxima Centauri is the same way a person standing at the edge of the ocean knows how wide the Pacific is. The number is real, the water is real, and neither the number nor the knowledge of it brings the other shore 1 centimeter closer. But there is a reason this particular star has occupied the imagination of scientists, engineers, and dreamers more than any other point of light in the sky. And that reason crystallized on a Tuesday morning in August of 2016, when the European Southern Observatory convened a press conference in its headquarters in Garching, Germany, and announced something that stopped the scientific community mid-breath. There was a planet, not orbiting some distant star, catalogued by a number in a database, not in some remote corner of the galaxy requiring decades of light travel just to reach with a signal, orbiting Proxima Centauri, the nearest star, 4.24 light-years away. A world with a mass comparable to Earth sitting at a distance from its star, where temperatures could under the right conditions allow liquid water to persist on a rocky surface. They named it Proxima Centauri b. The discovery had been years in the making. Astronomers at the European Southern Observatory had been monitoring the faint red star using a technique called Doppler spectroscopy, a method that detects not the planet itself, but the gravitational whisper it leaves on its star. As a planet orbits, its gravity tugs the star gently toward it, then pulls it gently away. That motion, imperceptible to any direct observation, shifts the wavelengths of the star's light in a pattern as regular and readable as a heartbeat. The signal from Proxima Centauri repeated with a period of 11.2 Earth days. A world with a minimum mass of approximately 1.07 times Earth's orbiting at a distance of roughly 7.5 million kilometers from its star. Because Proxima Centauri burns so much cooler and dimmer than our Sun, it is a red dwarf radiating only about 1/600th of the Sun's total energy output. That close orbit places Proxima b squarely within the habitable zone, the region of space where a rocky planet with an atmosphere of the right composition might hold liquid water on its surface. The region we have spent decades scanning the sky to find around other stars. And here it was, around the nearest one. The language practically assembled itself in every headline, every press release, every excited conversation in university corridors and observatory break rooms across the world. An Earth-sized world in the habitable zone of the closest star to our Sun. The discovery felt almost too convenient, as though the universe had placed the most tantalizing possible destination at the shortest possible distance and simply waited to see what we would do about it. What followed in the scientific literature was careful, rigorous, and in some respects sobering. Additional observations confirmed the planet's existence, and began to probe the conditions it might face. Proxima Centauri is not a gentle star. It is an active flare star, a category of red dwarf that periodically erupts in violent bursts of ultraviolet and X-ray radiation, some of them releasing energy equivalent to thousands of times the most powerful solar flares ever. Recorded from our own sun, these eruptions scour the space around the star with radiation intense enough to strip an unprotected atmosphere from a rocky planet over geological timescales. Whether Proxima b has retained an atmosphere, and whether any atmosphere that remains could shield a surface from that radiation, are questions that current telescopes cannot yet definitively answer. The planet is also almost certainly tidally locked. Proxima b orbits so close to its star that the same gravitational darkness, whether a world divided between eternal noon and eternal midnight, could distribute heat well enough to maintain habitable conditions somewhere along its terminator. The boundary between the two hemispheres depends on atmospheric dynamics that remain poorly constrained by observation. None of this diminishes the significance of the discovery. Finding a potentially habitable world orbiting the nearest star remains one of the most important results in the history of exoplanet science. But it does something else. It transforms Proxima b from an abstraction, a name, a classification, a point on a graph, into a specific and deeply uncertain destination. A place with conditions we cannot yet characterize. A world that might be everything the habitable zone label implies, or might be a scorched, airless rock whose brief claim to habitability ended billions of years ago under the relentless assault of its star's radiation. And all of this uncertainty sits at the end of 4.24 light-years of empty space. The nearest star is not close. It is merely the least far. Understanding what 4.24 light-years actually means requires leaving the comfortable abstraction of the number and forcing it through the filter of physical scale. Not mathematical scale, not powers of 10 on a graph, but the kind of scale you can walk across, drive through, or at least hold in your mind as a coherent image. Begin with light itself. Light is the fastest thing in the universe. Nothing with mass can reach its speed. Nothing we have ever built has come within a factor of thousands of its velocity. In 1 second, a beam of light travels approximately 299792 kilometers. In that same second, a commercial passenger aircraft flying at cruising speed covers roughly 250 meters. Light is not merely faster than everything else. It is faster than everything else by a margin that defies the ordinary vocabulary of speed. In 8 minutes and 20 seconds, light travels from the surface of the sun to the surface of the Earth. In roughly 5.5 hours, it crosses the orbit of Neptune, the outermost major planet in our solar system. In about 22 hours, it reaches the current position of Voyager 1, the most distant human-made object in existence, launched from Earth in September of 1977, and still traveling outward nearly 5 decades later. And then nothing. Empty interstellar space. A darkness interrupted only by the occasional lone hydrogen atom. For 4 years, 2 months, and 17 days, the light continues before it reaches the next star. 1 light-year equals approximately 9.46 trillion kilometers. Multiply by 4.24, and you arrive at roughly 40 trillion kilometers, or 25 trillion miles, a figure so large that the human brain processes it the same way it processes infinity, as an undifferentiated enormity that triggers awe without producing understanding. So build a model instead. Shrink the sun to the size of a basketball, a sphere about 24 centimeters across sitting on a table in front of you. At that scale, Earth becomes a small grain of sand, roughly 2 millimeters in diameter, orbiting 26 meters away from the basketball. Jupiter, the largest planet in the solar system, shrinks to a marble about 2.5 centimeters across, drifting 135 meters from the center. Neptune, at the outer edge of the known planetary system, becomes a smaller marble orbiting roughly 800 meters away. The entire solar system, every planet, every moon, every asteroid belt, fits within a sphere less than 2 kilometers across. Now, find Voyager 1-inch this model. After nearly 5 decades of continuous flight traveling at approximately 17 kilometers per second in real space, Voyager sits at roughly 165 astronomical units from the Sun. In the model that places it about 4.5 kilometers from the basketball on the table, still in the neighborhood, still close enough to walk to. And Proxima Centauri, at the same scale, the nearest star sits approximately 7,000 kilometers away, not across the room, not across the city, not across the country. The distance in this model from the basketball on your table to the nearest other star is roughly equivalent to the real-world distance from London to the southern tip of India. Everything humanity has ever explored, every planet visited by a probe, every moon mapped by an orbiter, every comet grazed by a passing spacecraft, fits within a sphere 2 kilometers across at this scale. The nearest star is 7,000 kilometers away. Voyager 1 has been flying for nearly 50 years. In our scale model, it has covered 4.5 kilometers. The nearest star is 7,000 kilometers away. That is not a gap that incremental improvement closes. That is not a problem that a better engine, more funding, and a committed program director resolves within a generation. That is a fundamental statement about where humanity stands in relation to the stars, and where we will likely continue to stand for a very long time. The nearest star is not close. It is merely the least far. Voyager 1 currently travels through interstellar space at approximately 17 kilometers per second. That figure is not an approximation or a rough estimate. It is a precisely measured velocity tracked daily by the Deep Space Network, a global array of massive radio antennae that still maintains contact with both Voyager spacecraft across distances that require signals traveling at the speed of light, roughly 22 hours to traverse. 17 kilometers per second is fast by every standard of ordinary experience. It is fast enough to cross the continental United States in roughly 4 minutes, fast enough to circle the Earth at the equator in just over 20 minutes. At that speed, Voyager would reach Proxima Centauri in approximately 7,300,000 years. Let that number settle. Not 73 years, not 730, 73,000 years. For context, 73,000 years ago, modern humans had not yet left Africa in significant numbers. The cave paintings at Lascaux, among the oldest known examples of human art, were painted roughly 17,000 years ago. The agricultural revolution, the development of farming that enabled permanent settlements, cities writing, and civilization began approximately 10,000 years ago. The entire span of recorded human history from the first Sumerian clay tablets to this moment encompasses roughly 5,000 years. Voyager 1 flying at its current speed would require almost 15 times the total length of recorded human civilization to reach the nearest star. Now, consider the fastest spacecraft humanity has ever built. The Parker Solar Probe, launched by NASA in August of 2018, uses repeated close flybys of the Sun to accelerate through gravity assists, reaching velocities during its closest solar approaches that no human-made object has ever matched. At perihelion, the closest point of its highly elliptical orbit, Parker briefly reaches speeds of approximately 191 kilometers per second, fast enough to travel from New York to Los Angeles in roughly 20 seconds, fast enough to circle the Earth in just over 2 minutes. At that peak velocity, the journey to Proxima Centauri would require approximately 6,700 years, faster than Voyager by a factor of 11, still longer than the span of time separating us from the construction of the Great Pyramid at Giza, repeated more than twice. And Parker Solar Probe achieves that speed only momentarily at the point of closest solar approach, where the Sun's gravity has been doing the accelerating. No spacecraft maintains anything approaching that velocity in open interstellar space. Parker's average speed across its full orbital period is a small fraction of its peak. In the unassisted emptiness between stars where there is no massive body nearby to provide gravitational acceleration, a spacecraft travels at whatever velocity its engines last gave it. These are not hypothetical calculations applied to imaginary vehicles. These are real spacecraft built by real engineers, performing real missions, traveling at the fastest speeds humanity has ever achieved in space. And they are nowhere near fast enough. They are separated from the speed required for a practical interstellar journey, not by a factor of 2 or 5 or 10, by a factor of hundreds to thousands, depending on what practical means in this context. If you define practical as reaching Proxima Centauri within a single human lifetime of roughly 80 years, the required cruise velocity approaches 5% of the speed of light, approximately 15,000 kilometers per second. Parker Solar Probe's peak speed is 191 kilometers per second. The ratio between where we are and where we need to be is close to 80 to 1, and Parker Solar Probe is the fastest thing we have ever built. The nearest star is not close. It is merely the least far. The gap between the fastest spacecraft in existence and the speed required for a practical interstellar mission is not primarily a problem of ambition or funding or political will. It is a problem of physics encoded in a mathematical relationship that every aerospace engineer learns early in their training and never fully escapes. It is called the Tsiolkovsky rocket equation, formulated in 1897 by a Russian schoolteacher and self-taught mathematician named Konstantin Tsiolkovsky, working alone in a small town called Kaluga, producing one of the most consequential and most brutal equations in the history of spaceflight. The rocket equation describes the relationship between a spacecraft's exhaust velocity, how fast the engine throws mass out the back, the ratio of the spacecraft's initial mass, including fuel, to its final mass after the fuel is burned, and the total velocity change the spacecraft can achieve. The relationship is logarithmic on one side and exponential on the other, and the consequence of that mathematical structure is this: to double the velocity change available to a spacecraft, you do not need to double the fuel, you need to square the mass ratio. Every increment of additional speed costs exponentially more fuel mass. And the fuel mass must itself be accelerated, which requires more fuel, which must itself be accelerated. The spiral has no clean exit. For chemical rockets, engines that combust liquid or solid propellants to generate thrust, the exhaust velocity is fixed by chemistry. The most energetic chemical reaction available for propulsion, the combustion of liquid hydrogen with liquid oxygen, produces exhaust velocities of roughly 4.4 kilometers per second. That ceiling is not an engineering limitation. It is a thermodynamic fact about the energy stored in chemical bonds. No improvement in combustion chamber design, nozzle geometry, or manufacturing precision can push a hydrogen-oxygen engine significantly beyond that limit, because the limit is not in the engine, it is in the fuel. At 4.4 kilometers per second of exhaust velocity, the rocket equation becomes devastating at interstellar scales. To accelerate a spacecraft to 1% of the speed of light, roughly 3,000 kilometers per second, using chemical propulsion, would require a mass ratio so large that the fuel would outweigh the spacecraft by a factor that exceeds the mass of entire planets. The calculation does not produce an engineering challenge. It produces an absurdity. Chemical rockets are the technology that carried human beings to the moon, placed rovers on Mars, and sent probes to every planet in the solar system. They are extraordinary machines. Against interstellar distances, they are approximately as useful as a rowboat pointed at the horizon of the Pacific. This is not a failure of the engineers who built them. It is the universe declining to make itself convenient. The answer to the rocket equation's tyranny has always been the same: go deeper into the atom. Chemistry releases energy by rearranging electrons in molecular bonds, the outermost loosest layer of atomic structure. The energy stored there is real but modest, like burning the paint off a house and calling it fuel. To reach the speeds interstellar travel demands, you must crack open something far more fundamental. You must reach into the nucleus itself. Nuclear fission, the splitting of heavy atoms like uranium-235 or plutonium-239, releases energy at the nuclear level rather than the chemical level. The difference in energy density is not incremental, it is transformative. 1 kilogram of uranium, undergoing complete fission, releases roughly 80 trillion joules of energy. The best chemical propellants release approximately 10 million joules per kilogram. Fission is 8 million times more energetic per unit mass than the best chemistry available. That ratio alone explains why nuclear propulsion has occupied serious engineering attention since the earliest days of the space age. and why it has never in any form left the atmosphere under its own power. The first serious attempt to translate nuclear energy into interstellar propulsion was not a laboratory experiment or a computer simulation. It was a design study conducted by some of the most brilliant physicists of the 20th century in the years immediately following the development of the hydrogen bomb, when the destructive potential of nuclear weapons was being systematically examined for constructive applications. Project Orion began in 1958 at General Atomics in San Diego. The concept was developed primarily by Ted Taylor, a nuclear weapons designer who had spent years at Los Alamos crafting the smallest and most efficient nuclear devices in the American arsenal, and Freeman Dyson, a theoretical physicist whose intellectual range extended from quantum electrodynamics to the furthest speculative edges of what technology might someday achieve. Together, they proposed something that sounds, from a contemporary vantage point, either visionary or insane depending on your tolerance for audacity. The spacecraft would be propelled by nuclear explosions, not the controlled burn of a reactor, not the measured release of a fission pile. Actual nuclear detonations, one after another, detonated behind a massive steel pusher plate attached to the spacecraft by a system of shock absorbers. Each explosion would slam the plate forward. The shock absorbers would smooth the impulse into sustained acceleration, and the ship would ride the succession of blasts like a surfer riding a series of waves, except the waves were nuclear fireballs, and the surfer was a spacecraft the size of an ocean liner. The physics worked. That was the remarkable thing. Dyson's calculations showed that a large Orion vehicle using thermonuclear pulse units, rather than simple fission bombs, could achieve exhaust velocities of roughly 15,000 kilometers per second and a total velocity change, sufficient to cruise at several percent of the speed of light. A fully developed interstellar Orion, in his most optimistic analyses, might reach the Alpha Centauri system in roughly 130 years. Still a multi-generational journey, but one that at least exists within the same order of magnitude as a human civilization's planning horizon. The engineering was not the obstacle. The obstacle was the 1963 Partial Nuclear Test Ban Treaty, which prohibited the detonation of nuclear weapons in space. Orion was not merely inconvenienced by this treaty. It was ended by it. You cannot build a spacecraft propelled by nuclear explosions if international law forbids detonating nuclear weapons in space. The physics remained valid, the politics made it irrelevant, but Orion planted a seed. It demonstrated that if the energy density of nuclear reactions could be harnessed for propulsion, in whatever configuration the engineering and the law might allow, the numbers for interstellar travel began to approach the merely extraordinary rather than the physically absurd. The question became whether a more controlled, more politically acceptable form of nuclear propulsion could achieve comparable performance. Between 1973 and 1978, a group of engineers and physicists associated with the British Interplanetary Society attempted to answer that question with the most rigorous interstellar mission study ever conducted. They called it Project Daedalus, and they spent 5 years producing a design so detailed that it included mass budgets, structural analysis, fuel acquisition strategies, and mission profiles for a one-way robotic flyby of Barnard's star, a red dwarf approximately 6 light-years from Earth. Daedalus used a concept called inertial confinement fusion. Rather than detonating large nuclear bombs, the design called for firing small pellets of deuterium and helium, 3 both isotopes capable of undergoing fusion reactions, into a reaction chamber where powerful electron beams would compress and ignite them, releasing energy in controlled microsecond pulses at a rate of 250 per second. The exhaust from these miniature fusion events would be directed by magnetic fields into a thrust stream, accelerating the spare. The design that emerged from 5 years of analysis was a 2-stage vehicle massing approximately 54000 tons at departure. The first stage carried 46000 tons of fusion fuel. The second stage carried roughly 4000 tons plus the scientific payload. The projected cruise velocity was 12% of the speed of light. At that speed, Daedalus would reach Barnard's star in approximately 50 years. Two details about Daedalus illuminate the scale of the problem with a clarity that no abstract discussion of energy budgets can match. The first is the fuel. Daedalus required helium-3, a specific isotope of helium with 2 protons and 1 neutron. Helium-3 does not occur naturally in meaningful quantities on Earth. The entire global supply accumulated over decades from the decay of tritium in nuclear warheads amounts to a few kilograms. Daedalus required tens of thousands of tons. The project designers, working through the implications with the methodical seriousness that characterized the entire study, proposed mining helium-3 from the atmosphere of Jupiter. This would require deploying robotic balloon platforms into Jovian atmosphere at crushing pressures, harvesting and processing the gas, and somehow transporting the product back to wherever the spacecraft was being assembled. The mining operation required to fuel a single Daedalus mission would itself constitute a civilization-scale industrial undertaking, demanding technologies and infrastructure that do not exist and have never been seriously designed. The second detail is what Daedalus was designed to do at its destination. It was designed to fly past. There was no deceleration phase, no orbital insertion, no extended study. Daedalus would scream through the Barnard star system at 3,6,000 kilometers per second, 12% of the speed of light, spending a brief window of hours in the vicinity of its target before continuing into interstellar space forever. The scientific payload would have approximately 200 days of warning before closest approach to deploy autonomous subprobes, conduct remote sensing, and transmit data back to Earth. The transmission would take 6 years to arrive. The probe itself would never stop. Daedalus was not a mission architecture for reaching another star. It was a mission architecture for glimpsing one, and it required a fuel supply that does not exist on a ship that cannot be built using technology we do not have. The nearest star is not close. It is merely the least far. Beyond fission and fusion lies the theoretical extreme antimatter propulsion. When a particle of matter meets its antimatter counterpart, they annihilate completely. Both masses convert entirely to energy in accordance with Einstein's equation relating mass to energy. No reaction known to physics releases more energy per unit mass. A perfect matter-antimatter drive would extract the maximum energy theoretically available from its fuel, achieving exhaust velocity approaching the speed of light itself. The numbers that result from this calculation are extraordinary. A spacecraft carrying just a few hundred grams of antimatter could theoretically achieve velocities that would bring Proxima Centauri within a journey of decades. The energy density is not merely better than chemical propulsion or nuclear fission. It is the upper limit that physics permits. There is no higher energy density possible. You cannot do better than annihilating mass entirely. The problem is not the physics. The problem is everything else. Humanity's total production of antimatter across all particle accelerators, across all of recorded history, amounts to approximately 20 nanograms, not 20 grams, not 20 milligrams. 20 nanograms, 20 billionths of a gram, produced at an energy cost so extreme that manufacturing even that quantity consumed far more energy than was stored in the antimatter itself. The efficiency of antimatter production using current particle accelerator technology is roughly 1 part in 10 billion. For every 10 billion joules of energy invested in the process, approximately 1 joule of energy is stored in the resulting antimatter. To produce even 1 gram of antimatter at current efficiency, rates would require an energy input comparable to the total annual electricity consumption of the United States operating every power plant in the country for that purpose, for several years. To produce the quantities needed for propulsion grams, then kilograms, eventually tons, would require particle accelerator infrastructure thousands of times larger than anything currently in existence, operating at energy budgets that dwarf entire national economies. And then you would need to store it. Antimatter cannot touch normal matter without annihilating. Every surface of every container, every dust particle, every stray molecule of gas that contacts stored antimatter destroys both itself and the antimatter in an instant of pure energy. Storing antimatter requires suspending it in electromagnetic traps, have magnetic bottles that keep the antimatter particles from ever reaching the container walls. Current laboratory systems have successfully stored charged antiprotons for over a year, and the ALPHA experiment at CERN has trapped tens of thousands of anti-hydrogen atoms simultaneously. These achievements are genuine and remarkable. They involve quantities measured in trillionths of a gram held in apparatus, occupying entire laboratory buildings, requiring continuous power and monitoring by teams of specialized physicists. A space-rated antimatter storage system, compact enough to fit within a spacecraft, to light enough to be accelerated toward interstellar speeds, robust enough to survive launch, vibrations, thermal cycling, radiation exposure, and decades of operation without the maintenance infrastructure of a particle physics laboratory does not exist. No engineering study has produced a credible design. The gap between storing anti-hydrogen atoms in a room-sized laboratory apparatus and storing kilograms of antimatter in a reliable flight container is not a gap in funding or engineering effort. It is a gap in fundamental capability that no extrapolation from current technology can bridge on any foreseeable timeline. Antimatter propulsion is the right answer to the interstellar problem, in the same sense that teleportation is the right answer to the problem of Los Angeles traffic. The physics does not forbid it. The path from here to there passes through territory so far beyond current capability that it provides no guidance for near-term planning. The nearest star is not close. It is merely the least far. In April of 2016, the physicist Stephen Hawking and the technology investor Yuri Milner stood before cameras in New York City and announced the most ambitious interstellar initiative ever funded by private capital. They called it Breakthrough Starshot. The concept was elegant in a way that the Daedalus study and the Orion calculations never quite managed to be, not because it was more powerful, but because it was more minimal. Instead of trying to solve the interstellar problem by building a bigger ship with a more energetic propulsion system, Starshot proposed abandoning the ship almost entirely. The payload would be a wafer, a gram-scale chip, a few centimeters across, carrying a camera, a power source navigation systems, and a laser communicator. This chip, called a star chip, would be attached to a sail of reflective material measuring roughly 4 meters across, weighing only a few grams. The combined mass of sail and payload would be under a few grams total. The propulsion system would not travel with the spacecraft. It would remain on the ground. A phased array of lasers combining to produce approximately 100 gigawatts of coherent directed power would focus its beam onto the sail. Photon pressure, the tiny but real push that light exerts on any reflective surface, would accelerate the sail to approximately 20% of the speed of light within roughly 10 minutes. The acceleration involved would reach tens of thousands of times the force of Earth's gravity. Any conventional spacecraft component would be destroyed instantly. But a gram-scale chip bonded to an ultra-thin sail, if designed to withstand the stress, might survive. At 20% of light speed, approximately 6,000 kilometers per second, the star chip would reach Proxima Centauri in approximately 21 years. Upon arrival, it would fly through the system at that velocity, with no capacity to decelerate, spending a matter of hours in the vicinity of Proxima b before continuing into interstellar space forever. The data it collected, images, spectral measurements, whatever its tiny instruments could capture during that brief encounter, would be transmitted back to Earth by laser. The signal would take 4 years and 3 months to arrive. The proposal captured the imagination in a way that no interstellar concept had since the early dreams of the space age. Here was a mission that could conceivably launch within a generation. Here was a target arrival date that children alive today might live to see. Here at last was an interstellar concept scaled not to the ambitions of a distant future civilization, but to the technology and budgets of the early 21st century. Yuri Milner pledged $100 million to develop the concept. A scientific advisory committee assembled names that included some of the most prominent figures in physics, astronomy, and aerospace engineering. Research programs were established at universities across the United States and Europe. Papers were published, prototypes were studied, problems were identified, and then the problems refused to be solved. The laser array presented the first wall. 100 gigawatts of coherent phased power, focused into a beam tight enough to illuminate a 4-meter sail at distances of millions of kilometers, requires not a single laser, but millions of individual laser elements operating in perfect synchronization, their phases aligned to within a fraction of the wavelength of light, their beams combining into a single coherent spot rather than dispersing into useless diffuse radiation. Laboratory demonstrations achieved phase locking with arrays of tens of lasers. Scaling to the millions required for Starshot involves engineering challenges in phase control, thermal management, and beam combining that have no demonstrated solution path at anything approaching the required scale. The sail presented a second wall, a material 4 meters across weighing only a few grams that can reflect nearly all incident light without absorbing enough energy to vaporize while surviving accelerations of tens of thousands of G and the subsequent decades of interstellar particle bombardment before reaching its destination does not exist. Research teams at Caltech and elsewhere explored ultra-thin silicon nitride membranes and other candidate materials. They produced small-scale prototypes measured in centimeters. A full-scale sail was never fabricated. The Starship itself presented a third wall, a functional camera power source navigation system and laser communicator capable of transmitting data across 4.24 light-years, all within a mass budget of roughly 1 gram, requires miniaturization beyond anything achieved in any field of electronics. Every component must also survive decades of cosmic ray bombardment that would progressively damage semiconductor circuits. Radiation-hardened electronics are bulkier and heavier than conventional components, not lighter. In September of 2025, Scientific American reported that Breakthrough Starshot had entered indefinite hold after spending approximately $4.5 million of its pledged $100 million. After 9 years of work, the project had advanced understanding of individual component technologies. It had not produced an integrated prototype. It had not produced a credible construction timeline. Multiple independent analyses estimated the actual mission cost, accounting for the laser array and ground infrastructure, in the range of $5 to $10 billion. And that figure assumed technological breakthroughs in laser arrays, sail materials, and gram-scale spacecraft that had not been achieved and could not be reliably scheduled. Breakthrough Starshot was not a failure of imagination or commitment. It was an honest collision with engineering reality. And the collision is instructive precisely because Starshot represented the most stripped-down possible version of an interstellar mission. No crew, no life support, no deceleration, no return, no ability to enter orbit or study the destination at close range. Just a chip and a camera flung past the nearest star at a fraction of light speed, to returning a few hours of data during a flyby that the probe itself would never remember because it has no memory, because it has no mind, because it is a gram of electronics on a plastic sail, and it is still 9 years into a well-funded program nowhere near ready to fly. That is where the interstellar problem stands today. The most minimal conceivable robotic mission to the nearest star, a one-way flyby with a payload, has a paperclip, has proven too difficult to build on the timescale of a decade with a budget of $100 million. Every version of an interstellar mission more ambitious than that is harder. Every version that adds deceleration, orbital insertion, extended study, or human crew is harder by orders of magnitude. The nearest star is not close. It is merely the least far. There is a way to frame the propulsion problem that makes it feel solvable. Present the technologies in sequence: chemical ion, fission, fusion, antimatter, a laser sail. Note that each is more capable than the last. Observe that human technology has a consistent history of achieving what once seemed impossible, and conclude that the interstellar problem is simply a matter of time and continued progress. This framing is not wrong. It is incomplete in a way that matters. The history of propulsion technology does show a trajectory of improvement, but the trajectory is not smooth, and the remaining distance to interstellar capability is not a continuation of the curve that has carried us from gunpowder rockets to ion drives. It is a discontinuity, a cliff. The jump from the fastest spacecraft ever built to a vehicle capable of reaching Proxima Centauri within a human lifetime requires not incremental refinement, but the practical demonstration of controlled nuclear fusion, a technology that, as of 2026, has not been achieved on Earth in any sustained form. The ITER experimental reactor, the largest fusion project ever attempted, is being constructed in southern France through a consortium of 35 nations, representing more than half the world's population. ITER's goal is to demonstrate that a fusion plasma can produce 10 times more energy than is required to heat and confine it, a scientific milestone, not an engineering product. The machine itself, when complete, will weigh approximately 230,000 tons. Its vacuum vessel stands over 11 meters tall and nearly 20 meters in outer diameter, enclosed within a cryostat nearly 30 meters across. It requires external power measured in hundreds of megawatts simply to operate its superconducting magnets. Under the most recently revised schedule, ITER's deuterium-tritium fusion experiments are not expected to begin until 2039. It is not a power plant. It does not produce electricity. It is a proof of concept evidence that the physics works at scale, which the physics already suggested it should. The distance between ITER and a fusion rocket engine is not a matter of miniaturization and optimization. It is a matter of solving an entirely different set of engineering problems. A fusion rocket must convert the energy of fusion reactions into directed thrust accelerating reaction products through a nozzle or magnetic exhaust system at extremely high velocity. ITER converts fusion energy to heat. The conversion of fusion energy to propulsive thrust requires plasma confinement geometries, magnetic field configurations, and thermodynamic efficiency calculations that are distinct from the tokamak design ITER uses. A space-rated fusion engine must be compact enough to fit within a spacecraft, light enough to be accelerated without consuming impossible quantities of fuel, and reliable enough to operate continuously for years or intermittently for decades without maintenance. No fusion rocket engine exists. No design has been selected. No flight test has been scheduled. No organization has committed to a timeline for producing one. This is the honest state of interstellar propulsion in the year 2026. The physics permits the crossing, the engineering has not achieved it, and the gap between permission and achievement is not a crack to be stepped over. It is a canyon whose far wall is not yet visible from where we stand. Speed is the problem everyone talks about. It generates the dramatic numbers, the impossible comparisons, the visceral sense of scale that makes interstellar distance feel like a physical law rather than an engineering challenge. Speed is where the conversation always begins, and in most popular discussions of interstellar travel, speed is where it ends, as though the only obstacle between humanity and the stars is a sufficiently powerful engine. It is not. Suppose, for the sake of argument, that the propulsion problem is solved. Suppose that a century from now, fusion drives are mature, reliable, and capable of accelerating a large vessel to 10% of the speed of light. Suppose the engineering has been done, the fuel acquired, the ship assembled in orbit over the course of decades, and the mission launched. The propulsion problem for the purpose of this thought experiment is behind us. What remains is everything else. A gram-scale robotic probe does not eat. It does not breathe. It does not develop cancer from decades of cosmic ray exposure. It does not experience loneliness or grief or the slow psychological erosion of knowing that every person it has ever known is aging and dying 4 light years behind it. It does not need water recycling or carbon dioxide scrubbing or emergency surgery or conflict resolution or a reason to keep going when the mission has consumed the only life it was given. It does not panic. It does not despair. It does not mutiny. Human beings do all of these things. They do them reliably, inevitably, and with consequences that no amount of careful crew selection, psychological screening, or mission planning can fully anticipate or prevent. And this is why the human problem, the problem of keeping biological organisms alive and functional across decades of transit through the most hostile environment accessible to human experience, may prove harder than the propulsion problem it follows. Not harder in the sense of requiring more energy, harder in the sense of being constrained by factors that physics cannot simply override. Biology has limits that no engine can change. Human tissue responds to radiation the way it responds to radiation regardless of how fast the ship is traveling. Closed ecological systems obey thermodynamic laws that do not yield to ambition. Machines wear out on timescales that material science can extend but not eliminate. These are not engineering challenges with engineering solutions waiting to be found. They are constraints imposed by the nature of matter and life, and any honest assessment of human interstellar travel must confront them directly. Begin with what greets the ship the moment it clears the heliosphere and enters open interstellar space. Galactic cosmic rays are not a theoretical hazard. They are a measured, continuous, omnidirectional flux of high-energy particles, primarily protons and heavier atomic nuclei, originating from supernovae, active galactic nuclei, and other violent astrophysical processes distributed throughout the Milky Way. These particles travel at significant fractions of the speed of light and carry kinetic energies that make them among the most penetrating forms of radiation known. When they strike biological tissue, they do not simply deposit energy and stop. They ionize atoms along their path, breaking molecular bonds, fragmenting DNA strands, and initiating cascades of secondary particles that spread biological damage far beyond the original track. A single heavy ion, an iron nucleus, accelerated to near light speed by some ancient supernova, can tear a path of destruction through a cell's nucleus that disrupts hundreds of DNA base pairs in a single pass. On the surface of Earth, the planet's magnetic field deflects many of the lower energy cosmic ray particles before they reach the atmosphere. The atmosphere itself absorbs the remainder, attenuating the flux by a factor of roughly 1,000 between the top of the atmosphere and sea level. The result is a natural radiation environment in which the average person receives approximately 2.4 millisieverts per year from all sources combined: cosmic rays, terrestrial radioactivity, radon gas, and medical procedures. In low Earth orbit aboard the International Space Station, the protective effect of Earth's magnetic field is reduced but not eliminated. Astronauts at orbital altitude receive roughly 160 to 320 millisieverts per year, depending on the phase of the solar cycle, which modulates the intensity of the local radiation environment. This dose rate, already 10 to 100 times higher than at sea level, is considered acceptable for missions of 6 to 12 months, because the health risks, though measurable, remain manageable within the context of a career spent primarily on Earth. In interstellar space beyond any planetary magnetic field, and far from the modulating influence of the Sun's own magnetic bubble, the full galactic cosmic ray flux delivers an estimated dose of approximately 400 to 600 millisieverts per year. Over a 40-year journey to Proxima Centauri at 10% of the speed of light, a crew member would accumulate a total radiation dose somewhere between 16 and 24 sieverts. That number requires context. A single whole-body dose of 5 sieverts delivered acutely all at once is lethal to approximately 50% of exposed individuals without aggressive medical treatment. 8 sieverts delivered acutely is lethal to nearly everyone. The interstellar dose is not acute. It is chronic spread across 4 decades of continuous low-level exposure. The body has time to repair some of the damage between exposures. The immune system responds. Cellular repair mechanisms work, but chronic exposure at these levels does not simply accumulate without consequence. It drives an elevated and sustained rate of cellular damage that the body's repair systems cannot fully match. Studies of atomic bomb survivors, uranium miners, radiation workers, and populations exposed to fallout from nuclear testing have produced a consistent body of evidence about the health consequences of chronic elevated radiation exposure. Above approximately 1 sievert of cumulative dose, measurable increases in lifetime cancer risk become statistically robust across large populations. Above several sieverts, the effects extend beyond cancer to include cardiovascular disease, accelerated aging of the immune system, and most consequentially, for a mission that depends on cognitive performance, measurable damage to the central nervous system. NASA's own research program, conducted partly aboard the International Space Station and partly using animal models at the Brookhaven National Laboratory's NASA Space Radiation Laboratory, has documented that exposure to heavy ion radiation, the most biologically destructive component of the galactic cosmic ray spectrum, causes persistent neuroinflammation in mouse models, accelerated degradation of hippocampal function, impaired spatial memory, and behavioral changes associated with anxiety and cognitive decline. These effects were observed at dose levels and dose rates comparable to those a human crew would experience during an interstellar transit. They were not reversible. They persisted for the remaining lifetimes of the animals studied. A crew member arriving at Proxima Centauri after 40 years of continuous galactic cosmic ray exposure would have received a cumulative radiation dose exceeding every safety standard ever established for human spaceflight by a factor of roughly 20 to 40. They would have navigated 4 decades of progressively elevated cancer risk, immune system degradation, and potential cognitive impairment, while being entirely responsible for operating a complex spacecraft with no medical support beyond what they carried with them. The obvious question is whether radiation shielding can solve this problem. The answer is that shielding helps, but at a cost that may be prohibitive, and with limitations that physics imposes, regardless of how much material you are willing to carry. Radiation shielding works differently for different types of radiation. Low-energy gamma rays and X-rays can be attenuated effectively by relatively thin layers of dense material. Lead, steel, or even water will stop them. Galactic cosmic rays are different. They carry so much energy that when they strike dense shielding material, they produce showers of secondary particles, neutrons, pions, and other fragments that can themselves penetrate deep into shielded volumes. This effect, called spallation, means that adding conventional dense shielding can actually increase the dose received by crew members in some energy ranges rather than decrease it. The shield becomes a source of secondary radiation. The optimal shielding material for galactic cosmic rays is hydrogen-rich water, polyethylene, or liquid hydrogen are the most effective options, because hydrogen nuclei absorb energy from incoming particles without producing dangerous secondary cascades. But effectiveness requires thickness. NASA research estimates that reducing the interstellar cosmic ray dose by roughly 50% would require approximately 20 to 30 centimeters of water-equivalent shielding surrounding the entire habitable volume of the spacecraft. For a crew habitat comparable in pressurized volume to the International Space Station, roughly 900 cubic meters of pressurized space, this shielding mass alone could reach several hundred tons. Every ton of shielding must be accelerated along with the ship, compounding the propulsion challenge explored in the previous section with brutal arithmetic. Active shielding concepts, electromagnetic fields that deflect incoming charged particles, mimicking the function of a planetary magnetosphere, have been studied as an alternative to passive mass shielding. The physics is valid in principle. A strong enough magnetic field will deflect a charged particle. The difficulty is that the highest energy galactic cosmic rays carry so much momentum that deflecting them requires magnetic field strengths, orders of magnitude, beyond what current superconducting technology can achieve at spacecraft. Iscalis. The superconducting coils required to generate such fields would add enormous mass, require continuous power to maintain near absolute zero operating temperatures across decades of operation, and represent a single point of failure whose consequences, loss of the entire shielding system, would be immediate and catastrophic. No active shielding system has been built. No engineering design has demonstrated feasibility for a crude interstellar application. The radiation problem has no known solution. It has research programs, speculative concepts, and the frank acknowledgement from NASA's own human research program that galactic cosmic ray exposure represents one of the most significant unresolved barriers to long-duration human spaceflight beyond the protection of Earth's magnetic field. Radiation is the hazard that arrives from outside the ship. The hazards that arise inside the ship are in some respects more insidious because they are the product of the ship's own necessary functions compounding over time in a sealed environment with no possibility of external correction. The International Space Station is the most sophisticated closed habitation system ever placed in orbit. It has supported continuous human presence since November of 2000, hosting crews of typically 6 to 7 people conducting research, maintenance, and operations across a pressurized volume of approximately 916 cubic meters. It is by every reasonable measure an extraordinary engineering achievement. It is also entirely dependent on Earth. The station receives between 8 and 12 cargo resupply missions per year from multiple providers. These missions deliver food approximately 2 kilograms per crew member per day. The station carries no meaningful capacity for food production. They deliver spare parts for systems that fail regularly, as all complex mechanical systems do. They deliver replacement filters for the atmospheric control systems, fresh water to supplement the station's water recovery systems, replacement components for the exercise equipment that crew members use to combat bone density loss and muscle atrophy in microgravity, and consumables ranging from hygiene supplies to replacement computer hardware. The station's environmental control and life support system represents the current state-of-the-art in closed-loop life support technology. In 2023, the addition of a brine processor assembly brought the water recovery rate to approximately 98%, a milestone that represented years of development work and was celebrated across the space, life sciences, community as a genuine advance. 98% water recovery means that for every 100 liters of water entering the recycling system through humidity, condensate, urine processing, and other sources, approximately 98 liters emerge as potable water. The remaining 2% is lost and must be resupplied from Earth. 2% sounds small. Across a 40-year interstellar transit, 2% of the water budget represents thousands of liters that cannot be replaced. There is no cargo mission. There is no supplemental delivery. Whatever the ship carries at departure is everything the ship will ever have, plus whatever its closed-loop systems can recover and retain. The gap between 98% closure and 100% closure is not an engineering refinement. It is the difference between a system that works with external support and a system that works without it. Those 2% represent real physical losses, water molecules that escape as vaporbind to surfaces, become incorporated into biological waste streams in forms that the current recovery technology cannot process, or simply drift into volumes of the ship that the collection systems do not reach. Closing that gap requires understanding and intercepting every pathway by which water leaves the recoverable loop. No system has achieved this. Biosphere 2, the most comprehensive attempt to build a self-sustaining, closed ecological system on the surface of Earth, failed to close its water, oxygen, and food loops, even with the benefit of unlimited solar energy, a planetary atmosphere surrounding the structure, and the ability to intervene from outside when things went wrong. Biosphere 2 was a 3-acre enclosed environment constructed in the Arizona desert in the late 1980s, designed to support 8 crew members in a fully sealed, self-sustaining biosphere for 2 years. It contained agricultural areas, a rainforest, a savanna, a desert, a small ocean, and a wetland, an attempt to replicate the functional complexity of Earth's biosphere at miniature scale. The crew entered in September of 1991. Oxygen levels began dropping almost immediately, eventually falling from the 21% of Earth's atmosphere to approximately 14%, equivalent to the oxygen concentration at an altitude of roughly 4,300 meters. The crew experienced fatigue, shortness of breath, and impaired cognitive function. Eventually, pure oxygen had to be injected from outside the sealed structure, violating the closure that the experiment was designed to demonstrate. Carbon dioxide fluctuated unpredictably, driven partly by seasonal microbial activity in the soil. Many of the animal and insect species introduced into the system died, disrupting pollination and pest control in the agricultural areas. Food production fell significantly short of the planned caloric supply. The crew experienced measurable weight loss and significant interpersonal conflict. The experiment that was meant to demonstrate the feasibility of closed ecological life support demonstrated instead how extraordinarily difficult the problem is, even under ideal conditions with Earth's full gravitational field. unlimited energy supply from the sun, and the knowledge that rescue was always possible. An interstellar vessel must achieve what Biosphere 2 could not in microgravity, powered by onboard reactors rather than stellar energy, without the ability to intervene from outside and without the option of ending the experiment early. Food production in space exists at the level of demonstration experiments rather than meaningful supply. The veggie plant growth facility aboard the International Space Station has successfully grown lettuce, radishes, kale, Chinese cabbage, and chili peppers in controlled chambers illuminated by LED arrays. Crew members have eaten some of what they grew, a genuine milestone and a moment of real psychological significance to those who participated. But the quantities produced are measured in grams per harvest cycle. The caloric contribution to the crew's diet is negligible. The station's food supply arrives entirely from Earth, packaged and processed before launch, consuming a significant fraction of the mass budget of every cargo mission. Feeding a crew of 50 people, a modest estimate for a mission that needs sufficient redundancy in human expertise and genetic diversity to survive multi-generational transit, requires producing roughly 1,00000 kilocalories per day every day, without interruption for the duration of the quote, voyage. Meeting even a majority of that requirement through onboard agriculture demands growing areas of several hundred to over 1,000 square meters with reliable lighting, controlled atmospheric composition, continuous water and nutrient delivery, pollination, management, pest control, harvest processing, and a complete absence of catastrophic crop failures across 40 or more years of continuous operation. One bad harvest on Earth raises prices at the grocery store. One bad harvest aboard an interstellar vessel initiates a caloric deficit that cascades through every aspect of crew health, cognitive performance, immune function, and social stability. Stored food reserves provide a buffer, but a buffer measured in months cannot absorb a crop failure that takes a year to diagnose and correct. The agricultural system must work, not usually, not most of the time, every season, every year, across the entire transit. No such system has been designed. No such system has been tested. The closest analogues, Biosphere 2, the Melissa project conducted by the European Space Agency since 1989, and various small-scale experimental gardens aboard the International Space Station provide valuable data and genuine progress. They do not provide a blueprint for a food production system that can feed dozens of people without external input for 4 decades. Medical care aboard an interstellar vessel presents a problem that has no solution within current or near-projected spaceflight capability. On the International Space Station, a crew member who suffers a serious medical emergency can be evacuated to Earth within hours. The station maintains a docked Soyuz or Crew Dragon capsule specifically for this purpose. Medical consultations with ground-based physicians are conducted in near real time with communication delays of approximately 1 second. The station carries a medical kit sufficient for minor procedures and stabilization, with the expectation that serious conditions will be evacuated. Remove the evacuation option. Remove near real-time communication. Place the crew 4 light-years from the nearest hospital with a one-way communication delay measured in years. Every medical scenario that might occur in a population of 50 people over 40 years must be diagnosed, treated, and resolved using only what the ship carries. This population over 40 years will experience cardiac events, strokes, appendicitis, kidney stones, gallbladder disease, dental emergencies that progress to serious infections if untreated, fractures, burns, traumatic injuries from accidents during maintenance work in a complex mechanical environment, surgical emergencies requiring intervention within hours, cancers elevated well above baseline rates by 4 decades of unshielded cosmic ray exposure, autoimmune disorders, neurological conditions, the full spectrum of chronic disease that develops in any human population over the course of decades. The ship's medical facility must be capable of addressing all of this. It must perform surgery in an environment, microgravity or artificial gravity generated by rotation, that introduces complications with no terrestrial parallel. Blood in microgravity does not pool in a wound. It forms floating droplets that obscure the surgical field and drift through the cabin atmosphere. Instruments must be restrained, the patient must be secured, the surgical team must manage its own orientation, while performing procedures that require the precise control of human hands in an environment that provides no gravity to anchor them. No human surgical procedure has ever been performed in space. The research necessary to establish safe surgical protocols in microgravity has barely begun. The ship's pharmacy must stock medications for conditions that cannot be fully anticipated. Pharmaceuticals degrade over time, some within years, others within months. Across a 40-year mission, the medications packed at departure will have long since passed their effective lifespans. Either the ship must manufacture its own pharmaceuticals, a capability that requires chemical synthesis, infrastructure, and raw material stocks that compound the mass and complexity problem, or the crew must manage medical conditions using supplies whose potency is a fraction of what it was at departure. Infectious disease in a sealed environment presents a specific category of risk that is poorly understood because human populations have rarely lived in the kind of total closure an interstellar vessel requires. Every pathogen that enters the ship's atmospheric loop stays there. An outbreak of a respiratory illness cannot be contained by quarantine in the conventional sense because the entire atmosphere is shared. Antibiotic-resistant bacterial strains, which evolve readily in environments where antimicrobial use is concentrated and consistent, could render the ship's antibiotic stores ineffective against common infections within years long before arrival. Studies aboard the International Space Station have documented that certain bacteria increase their virulence in microgravity, while aspects of human immune function are simultaneously suppressed, a combination that makes the closed environment of a spacecraft a more dangerous infectious disease context than any equivalent enclosed space on Earth. The nearest star is not close, it is merely the least far. Mechanical reliability over interstellar timescales presents a challenge that is easy to state and nearly impossible to solve. The International Space Station has been continuously occupied since November of 2000. In that time, it has experienced pump failures, computer failures, coolant loop failures, atmospheric system failures, structural cracks, air leaks, and equipment malfunctions too numerous to catalogue. Every one of these failures was resolved through some combination of crew repair, using spare parts delivered from Earth, remote troubleshooting with ground-based engineering teams available in near real time, and in several cases, emergency spacewalks, requiring specialized tools and expertise. The station's operational continuity depends not on the perfection of its systems, they are not perfect, but on the continuous availability of resupply expert support and the institutional memory of hundreds of engineers on the ground who have spent careers understanding the station's every quirk and failure mode. Strip away all of that, place the ship 4 light-years from Earth, give the crew whatever spares they carried at departure, and nothing more. Give them access to the wisdom of Earth's engineers only through messages that take 4 years and 3 months to send, and another 4 years and 3 months to receive a 9-year round-trip delay that transforms real-time troubleshooting into an exchange of historical documents. Every component that fails must be repaired or replaced using what is already aboard. Every spare that is consumed cannot be replenished. Every system that degrades must be maintained by crew members who may or may not have the specific expertise required, because no crew of any practical size can carry deep expertise in every discipline represented by the ship's systems. When the specialist in atmospheric control falls ill or dies, or is simply occupied with a simultaneous emergency elsewhere on the ship, the atmospheric control system must be managed by whoever is available. The longest continuously operating human-made systems in interstellar adjacent environments are the Voyager probes. Voyager 1 has been in operation for nearly 50 years. It is durable beyond any reasonable expectation. It is also extraordinarily simple by the standards of a crewed vessel. No moving parts in its primary structure. No life support instruments, drawing tiny amounts of power from slowly decaying radioisotope generators. Several of its instruments have already failed permanently. Its power output declines by approximately 4 watts per year. By the mid-2030s, it will likely lack sufficient power to operate any instruments at all. Voyager is dying slowly, and it is dying after 50 years of operation, with no moving parts and no life support. A crude interstellar vessel with pumps, compressors, valves, heat exchangers, rotating habitat sections, agricultural systems, medical equipment, propulsion systems, and the accumulated mechanical complexity of a small city would face component failure rates that no engineering analysis has ever seriously modeled across 40-year timescales. The ship does not need to fail catastrophically to kill everyone aboard. It needs only to degrade faster than it can be repaired. Seals that crack over years, bearings that wear without replacement stock, filters that clog when the materials to manufacture new ones run out, electrical systems that accumulate radiation damage over decades until their behavior becomes unpredictable, a crew that spends an increasing fraction of its time on maintenance and repair at the cost of food production, medical care navigation, and the 1,000 other tasks that keep people alive until the maintenance burden exceeds the available labor and the systems begin to fail faster than they can be addressed. This is not a dramatic death, it is a slow one, and it is the kind of death that careful engineering can delay, but cannot indefinitely prevent, because in a sealed system with finite resources and no resupply, every component that fails and cannot be replaced brings the system one step closer to a threshold below which it can no longer sustain the lives depending on it. The propulsion problem asks whether we can build an engine powerful enough to cross the distance. The human problem asks whether we can build a world durable enough to survive the crossing. These are not the same question. Solving one does not solve the other. And unlike the propulsion problem, which is at its core a problem of physics and energy, the human problem is a problem of biology, reliability, closure, and the hard truth that no self-sustaining system capable of supporting human life for decades without external input has ever been built, tested, or demonstrated to work. There is a category of problem that engineering cannot address. It does not appear in mass budgets or thrust calculations. It does not show up in radiation dose tables or life support closure ratios. It lives in the space between people, in the way human beings respond to confinement, to uncertainty, to loss, to the slow erosion of purpose across years of identical days in a sealed metal container, moving through absolute darkness at a speed that brings the destination no closer in any way the senses can register. Psychology is not a soft problem. It is not a secondary concern to be addressed after the real engineering is finished. In the history of long-duration isolated expeditions, psychological failure has ended missions that the hardware could have completed. It has killed people who had food, water, and air. It has destroyed communities that had every physical resource required for survival. And on an interstellar vessel where there is no rescue, no rotation of personnel, no ability to remove a destabilizing individual, and no endpoint visible within the lifetime of anyone aboard, the psychological problem is not peripheral to the mission. It is central to it, in the same way that the structural integrity of the hull is central to it. Begin with what we know. The most comprehensive study of human psychology in prolonged isolation and confinement is not a space mission. It is a ground-based simulation conducted in Moscow between 2010 and 2011 under the auspices of the European Space Agency and Russia's Institute of Biomedical Problems. It was called Mars 500. 6 volunteers, 3 Russian, 1 Chinese, 1 Italian, 1 French Colombian, entered a sealed facility of approximately 550 cubic meters on June 3, 2010. They remained inside for 520 days. The estimated duration of a round trip to Mars, emerging on November 4, 2011, they had no physical contact with the outside world. Communication was delayed to simulate the light speed lag of a real Mars mission, reaching a maximum of 20 minutes one way. They conducted simulated spacewalks, medical experiments, psychological assessments, and the routine maintenance tasks of a long-duration mission. The results were instructive in ways that the researchers had not fully anticipated. The crew did not break down. There was no dramatic failure, no mutiny, no psychological collapse. The mission, by the most visible metrics, succeeded. But detailed analysis of the physiological and behavioral data collected throughout the 520 days revealed patterns that should concern anyone designing a mission 10 times as long. Several crew members became progressively sedentary over the course of the simulation, reducing their physical activity far below the levels maintained in the early months. Sleep-wake cycles drifted, with some individuals showing delayed sleep phase patterns, staying awake progressively later, and sleeping progressively later, a disruption consistent with the loss of natural light cues that regulate circadian rhythms. Alertness and cognitive performance, measured through standardized tests administered throughout the mission, declined in several crew members over time. The declines were modest but measurable, and 520 days is approximately 1/44th of the duration of a 40-year interstellar transit. Mars 500 was a simulation. The participants knew it was a simulation. They knew the door could be opened. They knew their families were a phone call, not a 4-year signal delay away. They knew that outside the walls of their facility, Moscow continued its ordinary life, and that when the experiment ended, they would return to it. The psychological buffer provided by that knowledge is incalculable, because it is precisely the knowledge that a real interstellar crew would not have. The Antarctic winter-over experience provides a closer approximation to genuine isolation. Researchers stationed at facilities like McMurdo Station or Concordia Base in Antarctica during the winter months face months of genuine isolation, no resupply, no evacuation for non-life-threatening conditions, limited communication, and an environment hostile enough that leaving the facility means risking death. Studies of winter-over crews consistently document a phenomenon researchers call the third-quarter effect, a dip in mood, motivation, and group cohesion that tends to occur roughly 3/4 of the way through deployment, when the end of the isolation is visible, but not yet close enough to provide meaningful psychological relief. Irritability increases, social withdrawal increases. Minor interpersonal frictions that were managed smoothly in the early months of deployment begin to generate disproportionate conflict. Antarctic deployments last months. Submarine deployments among the most psychologically demanding regular operational assignments in any military last weeks to a few months. The Mars 500 simulation lasted 520 days. An interstellar mission to Proxima Centauri, at 10% of the speed of light, lasts approximately 40 years. The difference in duration between a submarine deployment and an interstellar transit is not a factor of 2 or 5, it is a factor of several hundred. And psychological research has no data, none from any source, on how human beings respond to genuine, inescapable confinement across timescales of decades. We are not extrapolating from a limited dataset. We are extrapolating from a dataset that ends at a duration roughly 2% as long as the mission we are trying to understand. The problem compounds when you consider not just the duration but the nature of the isolation. An Antarctic researcher knows where they are. They can look outside and see the landscape, alien and brutal, but still the landscape of Earth. They know that beyond the horizon their civilization continues. They can speak to family members in near real time. They can receive news, literature, music, the cultural productions of a civilization that has not stopped while they were away. The psychological thread connecting them to the world they came from remains intact, attenuated by distance, but not severed. An interstellar crew loses that thread, gradually then completely. In the first year of flight, communication with Earth is nearly normal. A few hours of signal delay, inconvenient but manageable. Family members are still recognizable as the people who said goodbye at departure. News from Earth is current enough to be relevant. The crew still inhabits psychologically, if not physically, the same world they left. In the second year, the delay extends to months. Conversations become exchanges of letters sent and received across growing intervals. The emotional immediacy of human contact begins to fade. News from Earth describes events that happened long enough ago to feel historical rather than current. By the fifth year, the one-way communication delay approaches several months. A message sent from the ship will receive its reply a year later. Parents who were alive at departure have aged 5 years, may have died. Children left behind are no longer the children who waved goodbye. The world has continued without the crew at the speed of human life, and the crew can observe only its echoes arriving years after the events that produced them. By the 10th year, the crew is functionally cut off. They exist in a communicative void, sending messages into a silence that returns responses a decade after the original transmission. Earth is no longer a place they can reach. It is a memory increasingly remote, connected to their present lives by a thread of light that takes years to carry even the simplest acknowledgement of existence. By the 20th year, the founding crew members are in the middle of their lives. Whatever they left behind, families, friendships, careers, the cultures and places that formed them, has been transformed beyond recognition by 2 decades of ordinary human change. Children are adults, parents are elderly or gone. The world has been reshaped by events that the crew experienced only as delayed reports, unable to participate, unable to influence, unable to grieve properly because the news arrived years after the moment had passed. The psychological concept of being untethered from home, a condition studied in Antarctic winter-over crews and long-duration astronauts, involves not just loneliness, but a specific form of existential displacement. The place you came from continues to exist, but it no longer contains the life you left. Your presence there has been replaced, as all presences eventually are, by the living forward motion of the people who remained. Returning would not mean returning to what you left. It would mean arriving as a stranger in a place that was once familiar. For an interstellar crew, this displacement is not a temporary condition, it is permanent. And it deepens with every year of flight, until Earth is less a home than a direction, a point of origin, from which they have been receding for longer than most human relationships last. The nearest star is not close. It is merely the least far. Interpersonal dynamics in small confined groups over long durations are poorly understood and inherently unstable in ways that short-duration studies cannot fully capture. Research from Antarctic stations, submarines, and simulated space missions documents a consistent pattern. Carefully selected, highly trained professionals develop friction in confinement. They form alliances and counter-alliances. They develop grievances that in the open social environment of ordinary life would be ventilated and resolved through the natural circulation of human contact, a change of scenery, a conversation with someone outside the group, the simple relief of physical distance from a person who irritates you. In a sealed vessel, none of these safety valves exist. The person who irritates you is at breakfast. They are at the workstation beside yours. They are in the corridor when you wake at 3 in the morning because you cannot sleep, you cannot leave, they cannot leave. Whatever friction exists between you, it must be managed, or it must be endured in the same enclosed volume, day after day, for decades. Studies of isolated groups consistently show that the ability to manage interpersonal conflict deteriorates over time, even when it begins at a high baseline. The social skills that function well for months begin to fray across years as the accumulation of unresolved minor grievances compounds with the psychological weight of confinement and the absence of new social inputs. People who liked each other at departure may have exhausted what the relationship had to offer by year 5, leaving 2 decades of proximity to negotiate without the lubricant of genuine affinity. No data exists for human group dynamics in genuine isolation across timescales of 10, 20, or 40 years. We have studies of months. We have simulations of slightly more than a year. The rest is extrapolation from principles developed in contexts so brief that they may not transfer at all to the timescale an interstellar mission demands. Every human community requires governance. Systems of authority, decision-making, conflict resolution, and resource allocation are not luxuries that civilized societies have added to human life for the sake of order. They are the mechanisms by which groups of people survive the accumulated solutions to the problem of coordinating behavior among individuals whose interests are not always aligned. On Earth, these systems evolved over millennia, supported by cultural traditions, legal frameworks, enforcement mechanisms, and the implicit pressure of neighboring communities whose existence provided both competition and comparison. On an interstellar vessel, none of those supporting structures exist. Whatever governance system is established at departure must function across decades, potentially across generations, in a sealed, permanent, inescapable community, where every person depends on every other person for survival, and where no external authority can arbitrate disputes, override bad decisions, or remove leaders who have become dysfunctional. The options available for structuring authority aboard such a vessel are all variations on arrangements that history shows to be unstable over long timescales in isolated conditions. A military hierarchy provides clarity of command and rapid decision-making in emergencies, qualities that a spacecraft operations environment genuinely requires. But military hierarchies depend on chains of accountability that ultimately extend back to an external authority, a civilian government, a chain of command with oversight mechanisms, the threat of legal consequences for abuses of power. Remove all of that, and a hierarchy becomes whatever its leader decides it is. Across decades, with no checks on authority and no exit available to those at the bottom of the structure, the risk of authoritarian calcification is not theoretical. It is historically documented in every isolated community that has ever operated under unchecked leadership. A democratic model offers broader participation in decisions and distributes power across the community in ways that reduce the risk of individual tyranny. But democracy, in a small sealed population, introduces its own failure modes. Factional disputes in a community of 50 people, where majority votes produce real winners and real losers, who must continue living side by side in close proximity, with no ability to withdraw, generate conflict that democratic theory was not designed to resolve. Democratic systems on Earth function partly because dissatisfied minorities can in principle leave, relocate, seek redress through external institutions, or at minimum create physical distance between themselves and those they disagree with. On an interstellar vessel, the minority faction has none of these options. They must accept the outcome of every vote, every policy decision, every allocation of resources, with no recourse other than compliance or disruption. And disruption aboard a spacecraft is not civil disobedience. It is a threat to everyone's survival. Leadership succession compounds every governance model. A mission lasting 40 to 100 years will outlast the functional careers of its founding leaders. The original commander will, age may become physically or cognitively impaired, will eventually die. Transferring authority in a sealed, isolated community with no external arbitration is historically one of the most destabilizing moments any society can face. Succession crises have ended civilizations on Earth, with the full resources of nations available to manage the transition. Aboard an interstellar vessel, a succession dispute does not merely destabilize the community. It threatens the physical survival of every person aboard because the ship's operation depends on coordinated technical management that governance failure can disrupt fatally. The nearest star is not close. It is merely the least far. The multi-generational mission, the generation ship, is the most commonly proposed solution to the travel time problem, and it deserves direct examination because it is often presented as though accepting its premises resolves the fundamental difficulty. The logic is straightforward. If no individual can survive the full transit, then build a ship capable of sustaining a community across multiple generations. The people who arrive at Proxima Centauri will be the grandchildren or great-grandchildren of the people who departed Earth. The journey becomes not a mission with a crew, but a civilization with a destination. The practical requirements of a generation ship exceed everything discussed in this account by significant margins. Supporting a population across generations, maintaining genetic diversity, sufficient to prevent inbreeding depression, sustaining cultural continuity across transitions that no living member can remember, providing education for children born in transit. Managing the demographic dynamics of births and deaths over decades requires a community of sufficient size that population geneticists and social scientists generally estimate at several hundred to a few thousand individuals as a minimum viable population. A ship carrying 1,000 people is not a spacecraft in any sense that current engineering can conceive. It is a space station the size of a small city, requiring agricultural capacity for 1,000 people, medical infrastructure for 1,000 people, educational systems, governance structures, and living spaces for a population whose psychological needs include privacy, community, meaningful work, and the formation of relationships across a full human lifetime. The mass and complexity of such a vessel is beyond any propulsion concept yet studied, and its governance challenges are beyond any social arrangement yet demonstrated to function over the timescales involved. But the deepest problem with the generation ship is not engineering or governance, it is ethical, and ethics cannot be solved by better design. The founding crew chooses to leave Earth. They understand the mission, they accept the conditions. Whatever the sacrifice, the permanent loss of everyone they have known, the decades of confinement, the radiation, the uncertainty about what awaits at the destination they have chosen it. That choice, however, constrained by the circumstances of the world they are leaving behind, is theirs. Their children did not choose. The children born aboard the vessel during transit entered a world defined entirely by decisions made before their existence. They were born into a community with a specific purpose, bound to a destination they had no voice in selecting in a vessel they cannot leave, moving toward a world they have never seen and may never reach away from a civilization they will never know directly. They will live their entire lives from birth to death in the sealed environment of a ship in transit. Earth is not their home. It is a concept, a story, a set of images transmitted across light years by people they have never met. Whether it is morally acceptable to create human lives under these conditions, lives without choice about their fundamental circumstances, lives defined by the ambitions and decisions of ancestors' lives that exist instrumentally as the means by which a future generation reaches a destination, is a question that philosophy has not resolved and engineering cannot address. There are serious thinkers who argue that the creation of a generation ship community constitutes a form of generational coercion, the imposition of a mission on people who did not and could not consent to it. There are others who argue that all human beings are born into circumstances they did not choose, and that the generation ship presents no unique ethical violation. Neither position has been settled, and the mission cannot be designed, funded, and launched without confronting the question directly. The nearest star is not close. It is merely the least far. There is one final dimension of the human problem that receives almost no attention in the technical literature, and almost all the attention in the science fiction that imagines interstellar travel. It is the question of purpose, of whether the mission can sustain the commitment of its crew, not just physically but spiritually across the decades of transit. When the destination is invisible behind them and the origin has faded to a point of light indistinguishable from the stars, the founding crew departs with a shared mission and shared identity. They are explorers, emissaries, the vanguard of humanity's expansion into the cosmos. That identity is powerful in the early years of flight, when the mission is fresh and Earth is still close enough to feel connected to. But identities sustained by narrative require the narrative to remain alive, and narratives about collective purpose have a way of losing their force when the people who created them age and die and are replaced by people who inherited the story rather than wrote it. The crew members born in transit, the generation ship's second generation, the children of the founding crew, did not choose the mission, they received it. And receiving a purpose is not the same as choosing one. A purpose imposed by inheritance carries a different psychological weight than a purpose freely selected, and that weight grows heavier as the transit continues and the abstract destination remains the only horizon the ship has ever known. What happens when a crew member, 50 years into a 40-year journey, perhaps simply stops believing that the mission is worth it, that the sacrifice is justified, that the world waiting at the end of the crossing is worth the world that was left behind? On Earth, a person who loses faith in their calling can change direction. They can leave their institution, redirect their energy, find new meaning in a different context. The physical freedom to change course is so fundamental to human psychological health that we rarely notice it until it is absent. Aboard an interstellar vessel, there is no new context available. The person who has lost faith in the mission must continue performing their duties regardless, because the survival of everyone aboard depends on collective function. They must maintain the life support. Systems tend the agricultural areas, perform their medical responsibilities, operate the navigation equipment, not because they believe in what they are doing, but because stopping would kill people who still believe. or people who are children and have no opinion yet, or people who are simply trying to survive the day. This is not a theoretical scenario. It is the logical endpoint of a mission that removes every exit and imposes every consequence on people who may not at some point in the crossing consent to the terms under which their lives are being spent. No screening process identifies this risk in advance. No psychological intervention resolves it once it develops. No governance structure accommodates it without coercion. The human problem in the end is not primarily a problem of biology or engineering. It is a problem of meaning, of whether any purpose can sustain a community of human beings across the full duration of a journey that exceeds every precedent for human endurance in a vessel that offers no escape and no alternative, toward a destination whose value cannot be confirmed until after every commitment has been made and every bridge has been burned. The nearest star is not close. It is merely the least far. Imagine you have solved everything discussed so far. The propulsion problem resolved. A fusion drive exists, mature and reliable, capable of accelerating a large vessel to 10% of the speed of light. The radiation problem managed to a degree that the crew can survive. The life support systems close their loops sufficiently to sustain the population across the transit. The psychological and social challenges navigated through some combination of careful design, governance structures, and human resilience that no one has yet demonstrated, but that optimism permits us to assume. The ship has been built, assembled, in orbit, crewed, and launched. 40 years have passed. The ship is now approaching the Proxima Centauri system, traveling at approximately 3,000 kilometers per second. At that velocity, it covers the distance from Earth to the Moon in roughly 13 seconds. It covers the distance from Earth to the Sun in approximately 1 hour and 23 minutes. It is moving at a speed so far beyond anything in ordinary human experience that the word fast has lost all useful meaning as a description of it, and it cannot stop. Not cannot as in the engines are broken. Cannot, as in stopping, was always the hardest part, and the conversation about how to stop has been quietly deferred since the earliest planning stages, because stopping requires almost exactly as much energy as accelerating the fuel to do it. Must be carried through the entire 40-year transit. And the mathematics of that requirement are so punishing that most mission architectures find it easier to simply not address the problem directly, to describe the acceleration phase in detail, hand-wave the cruise phase, and leave the deceleration page conspicuously thin. The deceleration problem is the part of interstellar mission planning that eats proposals from the inside. Consider the arithmetic first, because the arithmetic is where the problem lives. A spacecraft accelerating to 10% of the speed of light accumulates kinetic energy proportional to the square of its velocity. To shed that kinetic energy to decelerate back to orbital velocities at the destination requires removing it. Energy cannot be destroyed. It must go somewhere. On Earth, a car decelerates by converting kinetic energy to heat through friction in its brake pads. An aircraft decelerates by reversing thrust and generating aerodynamic drag against the atmosphere. Both methods depend on the presence of something to push against a surface, a fluid, a medium that absorbs the energy being shed. In interstellar space, there is almost nothing to push against. The interstellar medium contains approximately 1 atom per cubic centimeter on average. It is the closest thing to perfect vacuum that nature produces. There is no atmosphere to create drag. There is no surface to friction against. The ship arrives at its destination, carrying every joule of kinetic energy it accumulated during acceleration, and it must find a way to shed that energy, using whatever systems it brought with it. If the ship decelerates using onboard propellant firing its engines in reverse, throwing mass forward to push the ship backward, the rocket equation reasserts itself with full force. The ship must have carried the deceleration fuel through the entire 40-year cruise. That fuel is mass. Mass that had to be accelerated along with everything else during the departure burn. Mass that required its own fuel to accelerate. The exponential spiral that the rocket equation always produces reaches its most brutal expression in the round-trip problem. A ship that must both accelerate and decelerate, using onboard propellant, requires a mass ratio so much higher than a one-way flyby that the two designs are barely recognizable as variants of the same concept. Assign numbers to make this concrete. A ship that achieves 10% of the speed of light on a one-way flyby using a fusion drive with an exhaust velocity of roughly 10% of the speed of light, an optimistic but not physically absurd assumption for an advanced fusion system, requires a mass ratio of approximately 2.7. For every ton of dry spacecraft, the ship needs roughly 1.7 tons of fuel at departure. Now require the same ship to decelerate at the destination using the same drive. The ship must arrive at Proxima Centauri with enough fuel for the entire deceleration burn still aboard. Working backward through the rocket equation, the required departure mass ratio rises to approximately 7.4. For every ton of dry spacecraft, the ship now needs 6.4 tons of fuel. Extend this to a mission that decelerates at the destination and then returns a round trip, and the mass ratio climbs toward values that make the mission physically unrealizable, with any fuel source less energetic than antimatter. The exponential mathematics do not merely make the problem harder. At some point they make it impossible, because no realistic fuel density can provide the required energy within a mass budget that a spacecraft can carry. This is why Daedalus was designed as a flyby. This is why Breakthrough Starshot was designed as a flyby. This is why every serious interstellar mission study that uses onboard propulsion either limits itself to a flyby architecture or acknowledges the deceleration problem as the dominant design challenge without offering a credible solution. The flyby is not a compromise born of limited ambition. It is the only architecture in which the mathematics remain tractable. But a flyby is not a mission. It is a glimpse. A crew that has spent 40 years crossing the interstellar void arrives at Proxima Centauri, traveling at 10% of the speed of light. The known orbital radius of Proxima b is approximately 7.5 million kilometers from its star. At the ship's cruise velocity, crossing that distance takes roughly 7 minutes. The entire inner system, the space within which any habitable planet would orbit, would be transited in less than an hour. The crew gets a window of hours to observe their destination up close. Then the system recedes behind them at 3,000 kilometers per second and continues to recede forever, because there is nothing ahead of them and no way back. 40 years of transit for a few hours of observation, that is the honest outcome of a mission that solves the acceleration problem, but not the deceleration problem. And the deceleration problem, as we have seen, is in many respects harder than the acceleration problem, because it requires carrying the solution through the entire Triutlven, leaving it behind at departure. The nearest star is not close. It is merely the least far. Alternative deceleration concepts exist. They exist on paper, in theoretical physics journals, in the appendices of optimistic mission studies, in the whiteboard sessions of researchers who understand the problem deeply and are reaching for solutions at the edges of what current understanding permits. None of them have been built. None of them have been tested in space. None of them have been demonstrated at any scale that permits confidence about their behavior at interstellar mission scales. The magnetic sail, sometimes called a mag sail, is the most physically grounded of these alternatives. The concept rests on real physics. A loop of superconducting wire carrying an electrical current generates a magnetic field. Charged particles deflected by that field transfer momentum to the coil. In interstellar space, there is a sparse but real flux of charged particles, the stellar wind from nearby stars, the diffuse plasma of the interstellar medium that a sufficiently large magnetic field could interact with to produce drag. The ship would decelerate not by firing engines, but by deploying a magnetic field that acts as a brake against the medium it is moving through. The physics is not in dispute. The problem is scale and reliability. The braking force produced by magsail interaction with the interstellar medium is small. The interstellar medium is extraordinarily diffuse, and the momentum transfer from deflecting individual ions and protons is correspondingly tiny. To produce meaningful deceleration across the timescales relevant to an interstellar mission, the magnetic sail must be enormous loop diameters, measured in kilometers or tens of kilometers, maintaining a field strong enough to deflect particles across a large cross-sectional area. The superconducting coil must carry current without resistance across decades of operation, in a radiation-rich environment that degrades superconducting materials over time. The deployment mechanism must unfurl a structure potentially hundreds of kilometers across after decades of storage in the thermal and radiation environment of interstellar transit. The field must remain stable and coherent throughout the deceleration phase, which could itself last years. No superconducting magnetic sail has been built. No deployment mechanism for a kilometer-scale space structure has been tested. No analysis has demonstrated that superconducting materials can maintain their properties across decades of galactic cosmic ray bombardment in open interstellar space. The mag sail is a physically plausible concept. It is not an engineering design. It is a direction in which engineering might someday travel if the materials, science, the deployment technology, and the operational reliability questions are eventually resolved. Another proposed deceleration method uses the light of the destination star itself. For a laser sail spacecraft, one that was accelerated by a ground-based laser array during departure, it is theoretically possible to reconfigure the sail geometry upon approach to reflect photons from the destination star using their pressure to slow the spacecraft. Robert Forward, the physicist whose work on laser sails inspired the concept that eventually became breakthrough starshot, proposed a specific architecture in 1,984 inches, which the sail is split into two parts during approach, a large outer ring that is detached and remains on a flyby trajectory, while the inner portion uses photon pressure from the outer ring itself illuminated by the destination star to decelerate. The architecture is clever. The physics works in principle. The engineering is extraordinary, requiring the precise separation and coordination of a multi-component sail structure at interstellar distances, and the performance depends critically on the luminosity of the destination star. Proxima Centauri is the problem. Proxima Centauri emits approximately 0.00155 times the luminosity of our Sun. It is not merely dimmer, it is profoundly essentially dim, a star whose total energy output is so low that it cannot be seen with the naked eye from Earth, despite being the closest star to our solar system. The photon pressure available from Proxima Centauri at the distances relevant to approach and deceleration is negligible against any payload of meaningful mass. Forward's sail architecture was designed with brighter stars in mind. Applied to Proxima Centauri, the numbers that worked on paper against a sun-like star become inadequate by orders of magnitude against the faintest star within reach. Photon braking at Proxima Centauri works for very small payloads at very limited deceleration rates. It does not work for a crewed vessel. The nearest star is not close. It is merely the least far. There is a deceleration concept that sidesteps the problem of onboard fuel entirely by proposing to collect fuel from the interstellar medium in transit. The Bussard ramjet, proposed in 1960 by physicist Robert Bussard, imagined a spacecraft with an enormous electromagnetic scoop, hundreds or thousands of kilometers in diameter, that would collect hydrogen from the interstellar medium as it flew and feed it into a fusion reactor for propulsion. The ship would carry no fuel at departure. It would mine its propellant from the space it traveled through, accelerating indefinitely as long as it kept flying. The concept was elegant and inspired a generation of science fiction. It was also undermined by subsequent analysis. The interstellar medium contains roughly 1 hydrogen atom per cubic centimeter, on average far too sparse to provide useful propellant flow at realistically achievable scoop sizes. The drag produced by the electromagnetic scoop interacting with the interstellar medium would likely exceed the thrust produced by fusing the collected hydrogen at cruise velocities. The fusion of ordinary hydrogen, as opposed to the more energetic reactions involving deuterium or helium, requires conditions that no current or near-future fusion concept can achieve efficiently. And the scoop itself, a magnetic structure potentially thousands of kilometers across, faces the same engineering challenges as the mag sail, compounded by the requirement to operate continuously throughout the transit, rather than only during the deceleration phase. The Bussard ramjet is not a viable propulsion concept under current physical and engineering understanding. It is a beautiful idea that the mathematics did not support. Consider now the operational reality of deceleration. Even in the most optimistic scenario, a mission that carries onboard propellant for a retro burn accepts the mass penalty, solves the engineering, and arrives at Proxima Centauri with the fuel and functional engines required to slow down. The deceleration burn must occur at a specific time and place. Too early and the ship decelerates before reaching the destination, coasting into the system too slowly, or drifting wide of the target orbital insertion window. Too late, and the ship enters the planetary region at high velocity, with insufficient time to decelerate before passing through. The navigation required to execute a precise deceleration burn at interstellar distances after 40 years of transit, during which small positional errors compound through the laws of orbital mechanics, demands a precision that no spacecraft has ever demonstrated across comparable distances and timescales. The Voyager probes have been navigated with extraordinary precision across decades of flight, but they have not been required to execute a specific thrust maneuver at a specific point in space after 40 years of coast. They have simply drifted tracked from Earth, with course corrections applied during the early years of their missions when their reactors still produced sufficient power. A deceleration burn at Proxima Centauri is a different order of navigation problem. The ship must know exactly where it is. It must know exactly how fast it is moving and in exactly what direction. It must calculate the precise thrust vector and burn duration required to achieve a specific orbital insertion trajectory, and it must execute that calculation using navigation data accumulated across 40 years of transit, with error budgets that compound over time, and communication delays that prevent any real-time assistance from Earth. Celestial navigation at interstellar distances requires measuring the positions of stars with sufficient precision to determine the ship's location to within the accuracy required for orbital insertion. The techniques exist in principle. Stellar interferometry, pulsar timing, and other methods have been proposed for interstellar navigation. None have been validated at interstellar scales. None have been demonstrated in the operational environment of a spacecraft that has been traveling for 4 decades. And then the engines. The deceleration burn requires the ship's propulsion system to reignite and operate at full performance after the longest dormancy period ever demanded of any engineered system. If the mission has been cruising for 40 years, the fusion drive, or nuclear pulse system, or whatever propulsion architecture the mission uses, has been dormant or at reduced standby power for 4 decades. Turbo pumps, injectors, magnetic confinement systems, ignition mechanisms, every component of a complex propulsion system has been sitting in the thermal radiation and vacuum environment of interstellar space for 40 years, accumulating the slow damage of time. No rocket engine in history has been required to restart after decades of dormancy. The longest gap between firings for any spacecraft propulsion system is measured in years, not decades, and those restarts were treated as significant engineering events requiring careful analysis and monitoring. The Voyager spacecraft have not fired their thrusters for course corrections in years, and engineers at the Jet Propulsion Laboratory treat each thruster firing as a potentially unreliable event, carefully validating performance against expectations and treating anomalies with the seriousness they deserve. A deceleration burn at Proxima Centauri after 40 years of dormancy is not an event for which engineers on Earth can provide real-time support. The burn is occurring. The outcome is determined in hours. The message reporting the result takes 4 years to reach Earth. By the time anyone on Earth knows whether the deceleration succeeded or failed, the crew has already been living with the outcome for 4 years. If the deceleration system ignites and performs nominally, the ship begins to slow. The deceleration phase lasts months to years depending on the thrust profile, and during that entire period, the ship must continue to function life support, navigation, crew, health system maintenance, while simultaneously managing the complex dynamics of a large vessel under thrust in a gravitational environment it has never before encountered. If the deceleration system fails partially, if the thrust is lower than required, or if the burn must be terminated early due to a system fault, the ship enters the Proxima Centauri system at too high a velocity for orbital insertion. Depending on the severity of the shortfall, The crew may be able to perform a partial deceleration, using remaining propellant, settling for a high-velocity flyby rather than orbit. Or they may be unable to slow sufficiently for any useful observation window. Or they may be traveling too fast to safely navigate the inner system without risk of collision with planetary bodies they cannot avoid. If the deceleration system fails completely, if 40 years of radiation damage, thermal cycling and material degradation have rendered the propulsion system non-functional, the ship flies through the Proxima Centauri system at cruise on the velocity and continues into interstellar space on the far side. The crew is alive for however long the life support systems continue to function. They are in a vessel with no destination, no return trajectory, no rescue, and no propulsion. They are the most isolated human beings who have ever existed, surrounded by stars they cannot reach and moving away from the only star they were ever aimed at. There is no second attempt. The nearest star is not close. It is merely the least far. There is one more hazard of the transit that becomes acute during the deceleration phase, and it deserves direct acknowledgement because it is rarely discussed in proportion to its significance. At 10% of the speed of light, the interstellar medium is not the empty, nothing it appears to be from Earth. It is a particle field encountered at extraordinary relative velocity. A grain of dust massing 1 microgram, roughly the size of a fine particle of smoke, carries kinetic energy at 10% of light speed, equivalent to that of a small explosive charge. Even a single hydrogen atom encountered at that velocity delivers a measurable impulse. The continuous bombardment of a spacecraft traveling at interstellar speeds by even the sparse population of particles in the interstellar medium produces cumulative erosion of forward surfaces that no material currently in use for spacecraft construction can indefinitely withstand. During the cruise phase, the ship can orient itself to minimize cross-sectional exposure. It can carry sacrificial forward shields, bumper plates designed to ablate under impact, protecting the ship's critical systems behind them. These concepts have been studied, though not tested, at realistic interstellar velocities. During the deceleration phase, the ship's orientation changes. The engines which point forward during a retroburn face directly into the particle flux. Surfaces that were previously protected become exposed. The geometry of shielding must be reconsidered, adding operational complexity to a phase of the mission already demanding maximum performance from systems that have been operating for decades. None of this is insurmountable in principle. All of it adds layers of engineering complexity to a mission phase that the basic arithmetic has already made brutally demanding. The deceleration problem is not a footnote to the interstellar challenge. It is the challenge in its most concentrated form. All of the mass penalty, all of the propulsion difficulty, all of the mechanical reliability demand all of the navigation precision, all of the risk it converges at the moment when the ship must do the hardest thing it will ever attempt at. The end of the longest journey it has ever made, with the least margin for error it has ever faced, and with no help available from anywhere in the universe. Stopping is harder than starting. Arriving is harder than leaving. And the nearest star, which already demanded everything we have, and everything we might someday build just to reach, asks for something more still at the moment of arrival. It asks for perfection. And nothing built by human hands has ever been perfect. Suppose the ship stops. Suppose that after 40 years of transit, after the radiation and the silence and the mechanical attrition and the psychological weight of a journey longer than most human institutions survive, the propulsion system ignites on schedule and performs exactly as required. The deceleration burn proceeds nominally. The ship sheds its velocity over months of careful thrust management, navigating the approach with precision accumulated across 4 decades of careful celestial observation. The crew, or their children, or their grandchildren, whoever is alive at this moment, watches through the observation ports as the Proxima Centauri system resolves from a point of light into something with structure, with geometry, with the specific character of a place rather than a direction. The star comes into view first. Proxima Centauri is not what anyone raised under a sun-like star would recognize as ordinary. It is small, roughly 14% of the sun's diameter, a sphere that would fit inside a volume considerably smaller than the distance from Earth to the Moon. It glows a deep ruddy red, the color of cooling embers, rather than the warm yellow-white of our own star. It is dim enough that standing on the surface of its innermost planet, at the distance where Proxima b orbits the star, would subtend a slightly larger angle in the sky than our Sun does from Earth, but it would deliver far less heat and light. The illumination on Proxima b's surface, even in full daylight on the hemisphere facing the star, would be roughly equivalent to overcast conditions on Earth. Not darkness, not warmth. Something in bits out there, tinted deep red bathing, whatever landscape exists below in the color of an endless sunset. This is the destination. This is what 40 years of transit and centuries of human aspiration have been aimed at. A dim red star smaller than most people imagine when they hear the word star, orbited by a world whose conditions we have been trying to characterize from 4 light years away, using instruments that were not designed for the task, producing data that remains ambiguous on the questions that matter most. What do we actually know about Proxima b? The nearest star is not close. It is merely the least far. We know its mass with reasonable confidence. The Doppler spectroscopy signal that revealed Proxima b's existence constrains its minimum mass to approximately 1.07 times Earth's mass. The minimum because Doppler spectroscopy measures only the component of stellar motion along our line of sight, and a planet whose orbit is inclined relative to our viewing angle will produce a smaller apparent signal than its true mass would generate. The actual mass of Proxima b could be somewhat higher than the measured minimum depending on orbital inclination. It is likely a rocky world rather than a gas or ice giant. The mass range is consistent with rocky composition, and the orbital dynamics of the system make a very low-density planet at that distance unlikely. We know its orbital period, 11.2 Earth days. At that period it completes a full orbit around Proxima Centauri in less than half the time it takes Mercury to orbit our Sun. It is close to its star, close enough that the star's gravity has almost certainly synchronized the planet's rotation with its orbit, just as Earth's gravity synchronized the Moon's rotation with its orbit around us. This synchronization, tidal locking, is among the most consequential facts about Proxima b's potential habitability and among the most frequently misunderstood. Tidal locking means that one hemisphere of the planet permanently faces the star. The day side receives all of the stellar radiation, all of the light, all of the heat that the star delivers. The night side receives none. On the day side, the star never moves in the sky. It sits fixed at the same point above the horizon, or directly overhead if the planet's orbital geometry places the substellar point near the equator. From the moment the planet formed to the moment it is destroyed, when its star eventually evolves off the main sequence billions of years from now. The night side is in permanent darkness. Not the darkness of a terrestrial night interrupted by moonrise and the slow rotation of stars across the sky. Absolute perpetual total darkness, broken only by the light of whatever stars happen to be visible from that hemisphere, including at some point in the orbital cycle, the distant binary pair of Alpha Centauri A and B, which together contribute a combined brightness roughly equivalent to a very bright, full moon. Not enough to warm the surface, enough to see by dimly on a world that has never known a sunrise. Whether tidal locking is catastrophic for habitability or merely challenging depends almost entirely on one question. Does Proxima b have an atmosphere? An atmosphere does something more important than provide air to breathe. It distributes heat. On Earth, the atmosphere and oceans together transport enormous quantities of thermal energy from the equatorial regions, where solar heating is most intense, toward the poles where it is released into space. This circulation system prevents the tropics from becoming uninhabitably hot and the poles from becoming catastrophically cold. It moderates the temperature extremes that would otherwise make most of the planet's surface hostile to life. A tidally locked planet with a substantial atmosphere could in principle distribute heat from the permanent day side to the permanent night side through atmospheric circulation. The day side heats the atmosphere, which flows toward the cooler night side, releases its heat, cools, and returns to the day side. Computer models of tidally locked terrestrial planets suggest that under the right conditions, a sufficiently thick atmosphere with appropriate composition, this circulation could maintain temperatures on at least part of the night side above the freezing point of water and temperatures on at least part of the day side below the boiling point. A habitable zone might exist along the terminator, the boundary between the permanent day and permanent night hemispheres, or across a broader swath of the planet if circulation is efficient. These models are physically reasonable. They are also constrained by uncertainties so large that the range of outcomes spans from a genuinely habitable world to a completely uninhabitable one, with no clear way to distinguish between them from our current observational position. The uncertainty begins with the atmosphere itself. Whether Proxima b has retained an atmosphere after billions of years orbiting an active flare star is unknown. Proxima Centauri is not a stable, gentle energy source like our Sun. It is a flare star, a category of red dwarf, characterized by sudden violent eruptions from its surface. These flares are not the modest solar flares that occasionally disrupt communications on Earth. They are events of a different order entirely. The most energetic flares from Proxima Centauri release energy comparable to thousands of times the most powerful solar flares ever recorded from our own Sun, delivered to a planet orbiting at roughly 5% of the distance between Earth and our Sun. The consequences for a planetary atmosphere depend on whether the planet has a strong enough magnetic field to deflect the incoming particle streams. Earth's magnetic field, generated by the circulation of molten iron in its outer core, shields the planet's atmosphere from the solar wind, preventing the gradual erosion of atmospheric gases by the continuous flux of charged particles that our Sun produces. Without that magnetic shield, Earth's atmosphere would have been gradually stripped away over geological time, leaving behind a thin remnant insufficient to support complex life. Whether Proxima b has a magnetic field is unknown. Whether any magnetic field it might have is strong enough to protect its atmosphere against Proxima Centauri's much more intense and violent activity is unknown. The generation of a planetary magnetic field depends on the planet's internal structure, thermal history, rotation rate, and core composition factors that Doppler spectroscopy cannot reveal, and that no current or near-future telescope can directly measure. Red dwarf stars present an additional atmospheric threat beyond their flares. Young red dwarfs go through a prolonged pre-main sequence phase lasting hundreds of millions of years, during which they are significantly more luminous than they will be at maturity. During this phase, a planet in what will eventually become the habitable zone receives far more radiation than the habitable zone implies enough to drive a runaway greenhouse effect, boiling away surface water and driving water vapor high enough in the atmosphere for ultraviolet radiation to dissociate it into hydrogen and oxygen. The hydrogen escapes to space. The oxygen may react with surface rocks or escape as well, leaving the planet desiccated long before the star settles into its main sequence luminosity and the planet's location qualifies as habitable by temperature alone. Whether Proxima b experienced this early desiccation depends on the planet's water budget at formation and the specific timeline of Proxima Centauri's pre-main sequence evolution. Computer models suggest that planets forming in the outer regions of a red dwarf system and migrating inward could arrive in the habitable zone with enough water to survive the early desiccation phase. But this is a scenario of initial conditions that occurred 4 to 5 billion years ago, around a star we have been observing for only a few decades. The range of plausible outcomes is wide, and our observational leverage on it is narrow. A 2017 study using the Hubble Space Telescope measured the flux of ultraviolet radiation reaching Proxima b's surface during a period of enhanced stellar activity. The measured UV flux was approximately 100 times the ultraviolet radiation received by early Earth from our Sun. Whether this level of UV exposure is lethal to surface life, tolerable to life sheltered by several meters of water or rock, or somewhere in between depends on assumptions about atmospheric composition and thickness that remain unconstrained. Life on Earth includes organisms capable of surviving UV flux levels far higher than the global average through various protective mechanisms. Whether life could have originated and persisted on Proxima b under these conditions is a question that biology cannot yet answer from 4 light-years away. The nearest star is not close. It is merely the least far. In May of 2016, 3 months before the announcement of Proxima b's discovery, a team using the Australian Square Kilometre Array Pathfinder detected an unusually intense radio burst from the direction of Proxima Centauri. The event lasted only 2 minutes, but released energy comparable to one of the most powerful stellar flares ever observed. Analysis published in 2021 characterized this event as an extraordinarily energetic flare, releasing radiation across a broad spectrum, including millimeter-wave radio emissions that had never previously been detected from stellar flare. Events of this magnitude are not routine, but they are not unique either. Proxima Centauri is known to flare regularly, with moderate flares occurring multiple times per day and major events occurring several times per year. The cumulative effect of this activity on a planet at Proxima b's orbital distance over billions of years of stellar evolution has been the subject of intense modeling and debate. The modeling community has not converged on a consensus. Some studies conclude that the flaring activity is sufficient to strip most of a plausible initial atmosphere over timescales of hundreds of millions of years. Others conclude that a sufficiently thick initial atmosphere, combined with a moderate magnetic field, could survive the flaring environment over geological timescales. The disagreement is not about the physics. It is about the initial conditions, the starting state of the atmosphere, and magnetic field billions of years ago, which are not directly observable. What is observable from Earth with current and near-future telescopes is limited. The James Webb Space Telescope, the most powerful space telescope ever built, is in principle capable of detecting the atmospheric signature of a transiting exoplanet, measuring the way starlight filters through the planet's atmosphere during the brief period when the planet passes in front of its star, imprinting the chemical fingerprints of atmospheric gases on the transmitted spectrum. Whether Proxima b transits its star, as seen from Earth, is not confirmed. The planet's orbital inclination has not been directly measured. If the orbit is inclined by even a few degrees relative to our line of sight, no transit occurs, and the atmospheric transmission spectroscopy method cannot be applied. Alternative methods for characterizing Proxima b's atmosphere exist, but are at the frontier of current capability. Direct imaging of the planet in reflected starlight, possible with next-generation, extremely large telescopes currently under construction, might allow spectroscopic analysis of the planet's atmosphere in reflected light, rather than transmitted starlight. The extremely large telescope under construction in Chile by the European Southern Observatory is specifically designed with Proxima b as a priority target for direct imaging spectroscopy. First light for the telescope is projected for the late 2020s. If direct imaging observations succeed, they could reveal the presence or absence of major atmospheric constituents, carbon dioxide, water vapor, oxygen, methane, providing the first direct evidence about the planet's habitability. Or they could reveal an absence of atmosphere entirely, or a dense carbon dioxide atmosphere like Venus, or a composition that falls into none of our habitable or uninhabitable categories, cleanly requiring interpretation frameworks that current astrobiology has not yet developed. We do not know what Proxima b is. We know its approximate mass, its orbital period, and its distance from its star. We know the characteristics of its host star, including the radiation environment that star creates. Everything else, the presence of an atmosphere, the composition of that atmosphere, the surface temperature, the presence of liquid water, the geological activity that might replenish a stripped atmosphere, the magnetic field strength, the rotation state within the constraints of tidal locking predictions is unknown, modeled, contested, or simply unanswered. Now, place the mission in this context. A crew or several generations of crew has spent 40 years crossing 25 trillion miles of interstellar space. They have survived radiation doses exceeding every safety standard ever established for human spaceflight. They have maintained closed-loop life support systems that no technology demonstrator has ever proven can operate without external input across comparable timescales. They have managed the psychological and social challenges of permanent confinement and radical isolation in ways that no research program has ever studied at anything approaching this duration. They have navigated their vessel with sufficient precision to execute a successful deceleration burn at the far end of the longest journey in human history. They have arrived, and the world they have arrived to study may be airless. It may be a scorched rock, its atmosphere stripped by billions of years of stellar flare activity, its surface sterilized by ultraviolet radiation, intense enough to break apart the molecular bonds of organic chemistry. It may be a world where the day side has been baked to temperatures far above the boiling point of water, and the night side has frozen to temperatures approaching the liquefaction point of atmospheric gases, with no circulation system robust enough to moderate between these extremes because there is no atmosphere left to circulate. It may be none of these things. It may be a world with a thick nitrogen atmosphere, liquid water oceans on the twilight hemisphere, chemistry complex enough to have produced something recognizable as life. We do not know. And the mission that was designed to answer this question, the mission that consumed the resources, the lives, and the generational commitment of a civilization, discovers the answer only after every bridge has been burned and every option has been foreclosed. If Proxima b is habitable, the mission is vindicated. The sacrifice finds its meaning in the discovery. The crew or their descendants stands on the surface of another world for the first time in human history, beneath a dim red star in the light of an alien sky, knowing that what they have found justifies everything that was spent to find it. If Proxima b is not habitable, if it is the scorched remnant of a world that was never given the conditions life requires, then the mission has confirmed something true and important about the nature of the nearest stellar system. That confirmation has scientific value. It narrows the space of uncertainty about red dwarf habitability in ways that could inform future decisions about which stars to aim for next, if next is ever a word that means anything practical. But it does not give back the 40 years. It does not return the people who were born on the ship and never chose to be there. It does not restore the civilization that committed its resources and its ambition to this crossing, and arrived at a destination that cannot support what was brought to it. This is the final weight of the interstellar problem. The distance is not merely physical, the cost is not merely energetic, the risk is not merely mechanical. At the end of everything past the propulsion barriers and the radiation hazards, and the life support challenges, and the deceleration problem, and the decades of psychological endurance, there is an uncertainty so fundamental that no amount of preparation can resolve it in advance. We do not know what is there. We cannot know from here. We can only go and find out. And going costs everything. The nearest star is not close. It is merely the least far. Pull back now and see the full picture. Not one piece of it at a time. Not the propulsion problem in isolation. Not the radiation hazard examined separately from the life support challenge. Not the deceleration mathematics considered, apart from the question of what waits at the final destination. See all of it simultaneously the way an engineer responsible for the entire mission would have to see it the way an honest accounting of where humanity stands in relation to the nearest star demands it be seen. The mission requires a propulsion system capable of accelerating a large crewed vessel to a significant fraction of the speed of light. No such propulsion system exists. The most physically credible candidate, controlled nuclear fusion, has not been demonstrated to produce net energy output in any laboratory on Earth, despite decades of effort and the combined resources of the world's largest scientific institution. The experimental reactor that represents the current frontier of fusion research is a 23,000-ton machine, occupying a campus the size of a small town supported by 35 nations, scheduled to begin its primary experiments in 2039, at the earliest, and designed not to produce thrust, but to confirm that the physics of sustained fusion works at scale, a fact that the physics already suggested, but that engineering had not yet demonstrated. The mission requires energy budgets for acceleration and deceleration that, in the most optimistic scenarios built on technologies that do not yet exist, approach or exceed the total annual energy output of human civilization, not the energy budget of a space agency or a nation. The energy output of the entire species for years or decades directed entirely toward a single departure. The mission requires closed-loop life support systems that recycle water, oxygen, and food without net loss and without external resupply across timescales of 4 decades. The most advanced closed-loop system ever built recovers approximately 98% of water aboard the International Space Station and depends on regular cargo deliveries for everything else. The most comprehensive attempt to build a fully closed ecological system on Earth. Biosphere 2 failed to maintain oxygen levels, carbon dioxide balance, or food production within acceptable ranges, even with unlimited solar energy, planetary atmosphere surrounding the facility, and the ability to intervene from outside. The mission requires radiation shielding sufficient to reduce the cumulative galactic cosmic ray dose across 40 years of interstellar transit to levels that do not guarantee cancer, cognitive impairment, and immune system degradation in every member of the crew. No shielding solution has been demonstrated. The passive shielding mass required to provide meaningful protection would add hundreds of tons to a vessel already pushing the limits of conceivable propulsion technology. The active shielding concepts require magnetic field strengths beyond current superconducting capability and represent single points of failure whose consequences are total. The mission requires mechanical reliability from complex systems across timescales that no engineered system operating in a comparable environment has ever approached. The longest continuously operating human-made systems in space are simple, passive, and already dying. The mission requires psychological and social stability across timescales that no research program has studied and no isolated human community has ever demonstrated. The longest controlled isolation study ever conducted lasted 520 days in a facility with functioning exits and produced measurable cognitive and behavioral decline in multiple participants. The mission requires a deceleration system that performs its most critical function perfectly on the first attempt, after decades of dormancy at a distance from Earth, so great that no assistance is possible and no second attempt exists. And the destination, whose characterization justifies all of this, who the world at the end of the crossing, whose potential habitability makes the journey conceivable, remains uncharacterized on the questions that matter most. We do not know whether it has an atmosphere. We do not know whether it has liquid water. We do not know whether the radiation environment at its surface is compatible with the chemistry of life as we understand it. We know its mass and its orbital period. We know the color of its star. This is the honest picture. Not a council of despair physics does not forbid the crossing, and nothing in the catalogue of challenges described in this account violates any law of nature. But honest, every item in that list is a barrier that exists today in 2026, with no demonstrated solution and no credible timeline for resolution. Every item must be resolved, not independently but simultaneously, before a human mission to Proxima Centauri becomes a serious engineering proposition rather than a serious scientific aspiration. The nearest star is not close, it is merely the least far. There is a tendency when confronted with this catalogue to invoke the history of human technological achievement as evidence that the barriers will eventually fall. The argument is familiar and not without merit. A century ago, powered flight was barely 20 years old. 50 years ago, human beings had walked on the moon. 30 years ago, the internet did not exist as a public resource. The pace of technological change has been extraordinary, and the history of that change is full of moments where barriers that seemed absolute were revealed to be merely temporary problems, waiting for the right combination of insight, investment, and engineering ingenuity to dissolve them. This argument deserves to be taken seriously and then examined carefully, because the barriers confronting interstellar travel are not all the same kind of barrier, and distinguishing between kinds of barriers matters enormously for any honest assessment of when, if ever, they might be overcome. Some barriers are engineering barriers. They exist because we have not yet built the right thing, not because the right thing is physically impossible. Controlled fusion is an engineering barrier. The physics of fusion is well understood. The engineering of containing and sustaining a fusion plasma in a compact space-rated engine is not yet solved, but there is no physical law preventing it from being solved eventually. Closed-loop life support is an engineering barrier. The chemistry of recycling water and generating oxygen from carbon dioxide is known. The engineering of a system that does this reliably, without external input, across across decades has not been demonstrated, but the laws of thermodynamics do not prevent it. These barriers are real, and their timescales are uncertain, but they are in principle the kind of barriers that time and investment and engineering effort can erode. Other barriers are scaling barriers, problems that work at small scale, but break down when the scale required exceeds anything previously attempted by orders of magnitude. The laser array for breakthrough starshot is a scaling barrier. Phase locking a few dozen lasers works. Phase locking millions of lasers to produce a coherent 100 gigawatt beam is not a different version of the same problem. It is a qualitatively different problem that the scaling has created. Scaling barriers are harder than pure engineering barriers because they often reveal new physics and new failure modes that were invisible at smaller scales. The history of engineering is full of concepts that worked beautifully in the laboratory and collapsed under the weight of the scaling required to make them practical. Still, other barriers are fundamental barriers, constraints imposed not by current engineering capability, but by physics itself in ways that no amount of engineering ingenuity can circumvent. The rocket equation is a fundamental barrier of this type, not to propulsion in general, but to any propulsion architecture that must carry its own fuel. The exponential mass penalty of the rocket equation is not an engineering problem. It is a mathematical consequence of the physics of momentum exchange, and no clever engine design can make it go away. Working around it requires either leaving the fuel behind, as laser sails and ramscoops attempt with their own severe limitations, or using fuel with an energy density so high that the exponential penalty produces manageable rather than prohibitive mass ratios. Antimatter is the only fuel that meets this criterion, and the barriers to producing and storing antimatter in useful quantities are themselves combinations of engineering and scaling challenges, so severe that no timeline for their resolution can be honestly projected. And then there are the biological barriers, the constraints imposed not by engineering, but by the nature of human tissue and human minds. Galactic cosmic ray exposure is a biological barrier. The physics of high-energy particle interactions with biological tissue is well understood, and the interaction is destructive at the doses accumulated over interstellar transit timescales. Shielding can reduce the dose, but cannot eliminate it at masses compatible with a propelled spacecraft, and the body's repair mechanisms cannot fully compensate for chronic exposure at the levels that remain. This is not an engineering problem waiting for a clever solution. It is a constraint imposed by nuclear physics and radiobiology that no currently imagined technology can overcome within the mass and energy budgets available to a spacecraft. Distinguishing between these categories matters because the history of technological achievement, inspiring as it is, does not provide uniform evidence that all barriers fall equally. Engineering barriers have fallen with impressive regularity when resources and talent are applied. Scaling barriers have fallen more slowly and unevenly, and some have not fallen at all. Fundamental barriers have occasionally yielded to paradigm shifts, new physics that revealed the apparent barrier to be based on incomplete understanding, but they cannot be assumed to yield on any particular timeline, and they cannot be assumed to yield at all without the paradigm shift first. The barriers confronting interstellar travel include all three types intertwined in ways that make progress on any one of them conditional on progress on the others. A fusion drive that works does not solve the radiation problem. Radiation shielding that works does not solve the deceleration problem. Solving the deceleration problem does not solve the life support closure problem. Every barrier must fall, and most of them must fall simultaneously before the mission is viable. The nearest star is not close. It is merely the least far. It is worth being specific about what humanity has actually achieved in space, because the achievements are extraordinary and deserve accurate characterization, not inflation and not dismissal. We have placed human beings on the surface of the moon. 12 people walked on the moon between 1969 and 1972. The furthest any of them traveled from Earth was approximately 4,000,000 kilometers, roughly 1.3 light seconds. The moon is our only extraterrestrial foothold, and we have not returned to its surface since December of 1972. The Artemis program, designed to restore that capability, has been in development for more than a decade and has faced repeated delays. As of 2026, no crewed lunar landing has yet occurred under the Artemis architecture. We have sent robotic spacecraft to every planet in the solar system and to several moons, comets, and asteroids. The Voyager probes have crossed the heliopause and entered interstellar space, becoming the first human-made objects to do so. The New Horizons spacecraft flew past Pluto in 2015 and is now traveling through the Kuiper Belt. The Cassini spacecraft orbited Saturn for 13 years before its mission ended in 2017. The Mars Science Laboratory rover Curiosity has been operating on the Martian surface since 2012. The Perseverance rover has been collecting samples since 2021 in preparation for a future sample return mission. These are genuine achievements of the first-order evidence of what sustained engineering effort, focused resources, and institutional commitment can accomplish. Every one of these achievements occurred within a radius of approximately 50 astronomical units from Earth. Proxima Centauri is 268,770 astronomical units away. The ratio between the furthest reach of human robotic exploration and the distance to the nearest star is approximately 5000 to 1. The gap between our deepest solar system penetration and our nearest stellar destination is not the next step on a smooth curve of expanding reach. It is a discontinuity, a jump of more than 3 orders of magnitude that no extrapolation from current trends can bridge within any timeline that responsible planning recognizes as near-term. We have maintained continuous human presence in low Earth orbit since November of 2000 through the International Space Station. The station orbits at an altitude of approximately 400 kilometers, roughly 0.0013 light seconds from Earth's surface. It is resupplied multiple times per year. It can evacuate its crew to Earth in hours. It has never operated without external support for any duration longer than the gap between consecutive cargo missions, which is typically measured in weeks to a few months. We have demonstrated the ability to keep human beings alive in space for up to approximately 14 months. Continuously, the record set by Russian cosmonaut Valery Polyakov aboard the Mir space station in 1994 and 1,995, 14 months. A journey to Proxima Centauri at 10% of the speed of light takes approximately 480 months. The ratio between the longest duration any human being has spent in space and the duration of the transit to the nearest star is roughly 34 to 1, and the longest duration was achieved with continuous resupply and the ability to return to Earth at any time. These are the facts. Not discouraging facts, the achievements they describe are among the greatest in human history, but facts that define precisely and honestly the distance between where we are and where a human interstellar mission requires us to be. The nearest star is not close, it is merely the least far. There is a concept that appears occasionally in discussions of interstellar travel called civilizational scale. The idea that certain engineering challenges require not merely national effort or even international collaboration, but the organized commitment of an entire technological civilization. The construction of the Great Wall, the draining of the Zeta Z, the Apollo program, each represented a mobilization of resources at a scale that felt at the time at the upper limit of what human organization could sustain. Each was ultimately achieved. An interstellar mission may require civilizational scale in a sense that goes beyond even these precedents. Not because the resources are unavailable, the total productive capacity of human civilization applied to a single goal across a century is genuinely staggering, but because the timescales involved exceed the natural planning horizon of any human institution that has ever existed. Democracies plan in electoral cycles of 4 to 6 years. Corporations plan in quarterly and annual earnings cycles. Even the most long-lived human institutions, certain religious organizations, certain universities, certain family dynasties, rarely maintain coherent strategic commitment to a specific technical objective across more than a few generations. The Roman aqueduct system was built over several centuries, but it was built incrementally, each edition responding to immediate local needs rather than executing a plan conceived at the outset. The great cathedrals of medieval Europe took centuries to complete, but they were built by communities with continuous cultural and religious commitment to the same physical structure in the same location. An interstellar mission requires something different. It requires sustained, directed, technical, and financial commitment to a specific engineering objective across timescales that may span a century or more of development before departure, followed by a transit of 4 to 10 decades, by a mission at the destination whose results will not return to Earth for years or decades after they are generated. The total elapsed time from first serious engineering commitment to final scientific return could approach or exceed 2 centuries. No human institution has ever maintained coherent commitment to a specific technical objective across 2 centuries. The oldest continuously operating research institutions in the world, certain European universities, national observatories, geological surveys, have maintained their basic functions across this time span, but their specific research agendas have shifted with every generation of leadership responding to new discoveries, new priorities, and the natural turnover of the people and ideas that animate them. An interstellar program cannot shift its agenda. The ship once launched is committed to its trajectory. The mission once begun cannot be redirected by a new administration that has different priorities or a different theory of where humanity's resources should be aimed. This institutional challenge is not an argument against attempting the mission. It is an accurate description of a barrier that is as real as the rocket equation and as challenging as the radiation environment, and that receives far less attention in the literature of interstellar travel because it is not amenable to engineering analysis. You cannot solve the institutional commitment problem with a better engine design or a more energetic fuel. You can only solve it by building human institutions with a durability and coherence of purpose that has no historical precedent. The weight calculation that Andrew Kennedy formalized in 2006, the analysis showing that the optimal departure date for an interstellar mission lies decades to a century in the future, accounting for projected improvements in propulsion technology, contains within it an implicit assumption that is worth making explicit. It assumes that propulsion technology will improve at a rate sufficient to make waiting worthwhile. It assumes that the curve of capability extrapolated forward eventually reaches the threshold required for a practical interstellar mission within a time frame that human planning can address. That assumption may be correct. The history of technology provides some support for it, particularly for engineering barriers of the type that systematic research and development can erode. But the assumption is not guaranteed, and the weight calculation provides no guarantee that the crossing will ever be made, only a mathematical framework for deciding when to try, conditional on the assumption that trying becomes possible. The honest answer to the question of when humanity will send human beings to Proxima Centauri is we do not know. We do not know because the barriers are multiple and heterogeneous, and because progress on any one of them does not automatically produce progress on the others. We do not know because some of the barriers may be harder than they appear from our current vantage point, and some may be easier. We do not know because the institutional and civilizational prerequisites for such a mission lie as far outside our current capability as the engineering prerequisites, and no roadmap exists for developing them. What we can say with confidence is that none of the prerequisites, not one, has been met. Not the propulsion, not the life support, not the radiation solution, not the deceleration architecture, not the institutional framework, not the scientific characterization of the destination sufficient to confirm that the crossing would find what it was aimed at. We are at the beginning of the problem, not the middle, not the late stages where the solution is visible and the remaining work is implementation. The beginning, the stage where the full scope of the challenge is only now becoming clear, where the easy assumptions are being replaced by hard measurements, and where the distance between aspiration and achievement is being honestly mapped for the first time. That is not a failure. It is a recognition, and recognition in the history of every great human endeavor is where the real work begins. The nearest star is not close. It is merely the least far. Go outside tonight. Find a place where the sky is dark enough to see the stars clearly away from the light of cities, away from the familiar orange glow that has become the ceiling of most human lives in the modern world. Lie on your back if you can, let your eyes adjust. Wait for the sky to reveal itself fully the way it always has above every human being who has ever existed, from the first member of our species who looked up and wondered to the last one who will. What you are seeing is not the present. It is a collection of moments from the past, each arriving at a different delay, each star a message sent years or centuries or millennia ago, and only now completing its journey to your eyes. The light touching your retina left its source before you were born. In most cases, before anyone you have ever known was born, traveling through a darkness so complete and so vast that the human mind, confronted honestly with its scale, does not so much comprehend it as surrender to it. Somewhere in that sky, if you are in the southern hemisphere or close enough to the equator to see the constellation Centauri low on the horizon, there is a point of light too faint to see without assistance. You cannot find it with your naked eye. It glows at a visual magnitude of approximately 11.1, roughly 100 times too dim for unaided human vision to detect. It requires a telescope, even a modest one, to resolve from the background darkness. And yet, it is the closest star to our sun, the nearest point of light in all the cosmos beyond our own star, the destination that every serious interstellar mission concept in human history has ultimately used as its baseline, its minimum case, its proof that the journey is at least physically possible in principle. The light leaving that star right now will arrive at your eyes in 4 years, 2 months, and approximately 17 days. It has been traveling since before you began reading this account. It will still be traveling when you finish. And the star it came from, the nearest one, the closest possible destination, the least far point in an ocean of darkness that extends in every direction for distances that make the word vast sound like an understatement, is separated from you by 25 trillion miles of absolute nothing, requiring technologies we have not built, energies we have not harnessed, endurance we have not demonstrated, and a commitment we have not yet found a way to sustain. The nearest star is not close. It is merely the least far. Here is what this account has tried to do honestly, and what it has not tried to do. It has not tried to argue that human beings will never reach the stars. Nothing in the laws of nature prevents the crossing. Physics does not forbid it. The speed of light is an upper limit that becomes relevant only at velocities far higher than anything this account has discussed. The energy released by nuclear fusion is real and enormous, and in principle available to a civilization that learns to harness it efficiently for propulsion. The biology of human beings is fragile but adaptable, and the history of life on Earth is a 40 billion year demonstration of how resilient chemistry can be when given time and the right conditions. None of the barriers catalogued in this account are permanent in the way that physical laws are permanent. They are barriers of engineering and biology and institutional endurance, harder than they appear, slower to fall than optimism suggests, but not in principle immovable. What this account has tried to do is describe with the precision that the subject deserves where humanity actually stands in relation to the nearest star, not where we might stand someday under assumptions that cannot currently be evaluated, not where we stood in the imagination of a generation raised on science fiction that made the crossing feel inevitable. Where we stand now in 2026 with the propulsion technology, we have the life support systems, we have the radiation solutions, we have the institutional frameworks we have, and the characterization of the destination that we have. We stand at the shore, the water is real, the other shore exists, the crossing is not forbidden, and we have not yet built a boat. The achievements of human space exploration deserve to be named clearly because they are extraordinary, and because their extraordinary nature makes it all the more important to be honest about what they do not represent. In 65 years of spaceflight, we have placed machines in orbit around every planet in the solar system. We have landed on the Moon, on Mars, on an asteroid, on a comet, on Titan. We have sent probes past the heliopause into interstellar space. We have built and continuously occupied an orbital laboratory for more than 2 decades. We have deployed a space telescope that sees light that left its source before the Earth existed. We've detected gravitational waves from colliding black holes, photographed the shadow of a supermassive black hole in a galaxy 55 million light-years away, and discovered thousands of worlds orbiting other stars. These are not small things. These are among the greatest achievements in the history of our species, and they represent the accumulated effort of hundreds of thousands of scientists, engineers, mathematicians, technicians, and administrators working across generations with sustained purpose. They are what human ambition looks like when it is organized, funded, and aimed at something difficult. And every one of them, every probe, every landing, every telescope, every detection, was accomplished within a radius of approximately 165 astronomical units from Earth. Proxima Centauri is 268770 astronomical units away. The entire domain of human exploration, everything we have ever touched or reached or seen up close, occupies less than 1/10 of 1% of the distance to the nearest star. We are extraordinary. We are also very small. Both of these things are true simultaneously, and the tension between them is not a contradiction to be resolved. It is the condition of being human, possessed of minds large enough to measure the cosmos and bodies too fragile to cross it, living on a world just barely large enough to launch us, and just barely close enough to a star to keep us warm, looking out at a universe that operates at scales so far beyond our experience that every metaphor we reach for comes back inadequate. The nearest star is not close, it is merely the least far. There is a particular quality to the light of Proxima Centauri that matters here at the end of this account more than any technical specification. It is old light. The photons reaching your eyes tonight, if you could see them, if the star were bright enough to reveal itself without a telescope, departed their source more than 4 years ago. They were emitted by a nuclear reaction occurring in the core of a red dwarf star. In the time before you read this sentence, before the particular moment you are living through now had arrived or been anticipated or been given its specific character by the events that produced it. The star does not know you are here. The light does not know it is being observed. It has simply been traveling at the only speed it knows, through the only medium available to it, arriving at your eyes as a consequence of physics that cares nothing about meaning and everything about distance. And yet you are here. You exist in a universe that produced among its billion trillion stars and its incomprehensible spans of empty space at least one small world with at least one species capable of looking up, measuring the distance to a point of light too dim to see, calculating the energy required to reach it, cataloguing every barrier between here and there, and sitting with the full weight of that accounting without looking away. That is not a small thing. That may be the most remarkable thing in the observable universe, though we cannot confirm this and should hold the claim humbly. But consider what it represents. The universe is approximately 13.8 billion years old. For the vast majority of that time, it contained no mechanism for knowing itself, no system capable of gathering information about the cosmos and asking what it means. The stars burned without witnesses. The galaxies collided without observation. The light traveled without eyes to receive it. And then, on at least one small world orbiting an unremarkable star in an outer arm of an average galaxy, chemistry became biology. Biology became thought, and thought became the universe's first instrument for measuring its own scale. We are that instrument, imperfect, fragile, brief, constrained by biology that radiation damages and time exhausts, living on a world that will itself be uninhabitable in a few billion years when our sun expands and warms beyond the range of liquid water, separated from the nearest other star by a distance so vast that every speed we have ever achieved is irrelevant against it, and yet here measuring, here calculating, here confronting the full scale of what we cannot yet cross, and choosing to understand it rather than look away. The nearest star is not close. It is merely the least far. 4.24 light-years, 25 trillion miles, 268,770 astronomical units, 73,000 years at Voyager's speed, 6,700 years at the fastest speed any human-made object has ever reached, decades at best with propulsion technology that does not yet exist aboard a vessel whose life support has never been demonstrated to work. carrying a crew whose psychological endurance across the required duration has never been studied, aimed at a destination whose habitability remains unknown. These are the numbers. They are not arguments against the stars. They are measurements of the ocean between us and them, the most honest description currently available of what the crossing actually costs. There is a version of this story that ends here, with the accounting complete, and the conclusion drawn, in the nearest star, is beyond practical reach. The barriers are too numerous, the timeline too uncertain, the cost too high. That version of the story is wrong, not because the accounting is inaccurate, it is as accurate as current knowledge permits, but because the accounting describes where we are, not where we will always be. It describes the state of human capability at a specific moment in the history of a species that has been spacefaring for less than a single human lifetime, and that has already, in that brief period, reached every planet in its solar system and begun to characterize the planets of other stars. The other version of the story, the one that ends with humanity inevitably crossing the void, reaching Proxima b, standing beneath a red dwarf sun on the surface of an alien world, is equally premature. That version requires breakthroughs that have not occurred, sustained commitments that have not been made, and solutions to problems that have not been solved. It requires more than ambition. It requires time and patience, and the particular kind of honesty that can hold the full scale of what is not yet possible without either despair or false confidence. What remains between the premature despair and the premature triumph is the condition we actually inhabit. A species at the very beginning of its reach into the cosmos, possessed of instruments powerful enough to see the edges of the observable universe and propulsion systems powerful enough to cross the solar system, standing at the shore of an ocean that is real, whose far side exists and which we have not yet learned to cross. That is where we are. Not at the end of the story, not even near the middle. At the beginning, the chapter where the scale of the problem becomes clear for the first time and the work of actually solving it has barely begun. Go outside tonight. Look up at the place in the sky where a point of light too faint to see is completing a journey of 25 trillion miles toward your eyes. It left its source before this moment existed. It has been traveling through a darkness so vast and so cold that no scale model fully communicates what it contains. It arrives at your eyes as a photon absorbed by a molecule of rhodopsin in your retina, triggering a cascade of electrochemical signals that your brain interprets as the faintest possible impression of light, a signal below the threshold of visibility, detectable only with instruments present only as a fact rather than an experience. Somewhere beyond that invisible point of light in the dim red warmth of a star too faint to see a world is orbiting, we do not know what is on its surface. We do not know whether its atmosphere, if it has one, contains the molecules that life requires. We do not know whether the radiation from its star has sterilized it, or whether some chemistry persists there, patient and unreachable, waiting for an observation that has not yet been possible to make. We know it is there. We know its mass and its orbit and the color of the star it circles. We know the distance to it with extraordinary precision and the cost of crossing that distance with extraordinary clarity. We know that nothing we have built can reach it within a human lifetime, and that building something that can will require much more of us, more time, more understanding, more commitment, more endurance than anything we have yet attempted. We know we are looking at the nearest one. That is enough for now. Not enough to cross. Not enough to know what waits there, but enough to understand what the question is, and what answering it will require, and why the question matters in the way that all genuine questions about the nature of the universe matter. Not because the answer will be comfortable, but because the asking of it is among the most distinctly human things a species can do. The light is traveling. You are here. The distance between you and the nearest star is exactly what it is, not less because we wish it, not more because we fear it. 25 trillion miles of absolute darkness, and at the far end of it, a dim red star orbited by a world we cannot yet reach and cannot yet read, emitting light that has been traveling toward you since before this moment was to imagined. It arrives tonight, as it has every night, as it will continue to arrive whether or not we ever find a way to follow it home. The nearest star is not close. it is merely the least far. And someday, in a century, or 5 centuries, or a millennium, in whatever form human ambition eventually takes, when it has learned everything the crossing requires, that distinction may cease to matter. Not yet. But someday,